Rogue planets. Imagine stepping outside and looking up at the night sky, but instead of stars guiding your eyes, there is nothing. Total blackness. No sunrise, no sunset, no moon to cut the darkness. Just a world adrift, forever wandering through an endless void. That is what life would be like on a rogue planet, a planet with no home star, no parent sun to hold it close. These worlds exist, and not just one or two. Astronomers believe there could be more rogue planets than stars in the entire galaxy. Think about that for a second. Billions of stars scattered across the Milky Way, and still, the lonely drifters might outnumber them. It feels impossible, right? Planets without suns. But they are real. And here is the shocker. Some of them might be bigger than Jupiter. Imagine a world 10 times the mass of Earth, maybe even closer to Neptune in size, floating in the dark like a ghost ship. These giants are ejected from their original solar systems through violent gravitational battles. Maybe they got too close to another star. Maybe a larger planet kicked them out in a cosmic game of billiards. Whatever the reason, they were cast away. And now they wander, invisible against the black, completely untethered. And here is the part that messes with our intuition. These worlds are not automatically dead. At first glance, you might assume that without a star, without that constant stream of light and warmth, a planet would be nothing more than a frozen rock. But that is not always the case. Some rogue planets are thought to have thick atmospheres, with pressure so intense it traps heat deep inside. Others may carry vast oceans buried beneath layers of ice, kept liquid by the same geothermal forces that heat our own planet from the inside. In other words, just because they drift in darkness does not mean they cannot host conditions for life. This is where the story gets validating, because it lines up with what we already know about Earth. Our world is not just warmed by the sun. Beneath our feet, the Earth's core burns with energy left over from its violent birth, plus radioactive decay that constantly releases heat. That inner fire keeps tectonic plates moving, drives volcanic eruptions, and powers hydrothermal vents on the ocean floor. And here is the kicker. At those vents, life thrives. Entire ecosystems survive in total darkness, feeding not on sunlight, but on chemical energy from the planet itself. That is proof. If it happens here, why not on a rogue planet where the only warmth comes from below? Think about the implications. Somewhere out there, hidden in the dark, could be entire biospheres that have never seen a star, creatures that have no concept of night or day, oceans that never reflect moonlight, landscapes frozen above but alive below. And since rogue planets are nearly impossible to detect, these worlds could be passing right through our galactic neighborhood without us even realizing it. Astronomers only spot them when they bend the light of background stars, a technique called gravitational microlensing. That is how we know they are out there. But for every one we detect, countless others slip past unnoticed. Now, here is something even stranger to picture. If you were standing on the surface of one, the sky would be utterly empty. No sunrise, no blue gradient, just an eternal, suffocating dark. You would hear your own breath, maybe the crunch of frozen ground beneath your boots, but you would not see your hand unless you carried your own light. And yet, beneath that bleakness, the planet could hold a subsurface ocean kept warm by internal heat. Some scientists even speculate that thick hydrogen atmospheres could insulate a rogue planet so well that surface oceans might remain liquid. Imagine paddling a boat in the middle of nowhere with no sun overhead, just black sky. It is a nightmare, but also a dream of possibility. Here is why this matters to us on Earth. The idea of rogue planets stretches our imagination of where life can exist. We used to think life required the Goldilocks zone, that narrow band around a star where conditions are just right. But rogue planets laugh at that idea. They say life might not need a star at all, and if life can exist in places we once wrote off as impossible, then the odds of us being alone in the universe shrink even further. And do not forget, these wanderers are not locked into one region of the galaxy. They drift, they roam. Over millions of years, they could cross vast interstellar distances. That means if life does develop on a rogue planet, it could hitch a ride across the cosmos, potentially spreading to new star systems when conditions align. Suddenly, rogue planets stop being just cold drifters and start looking like seeds of life itself. Now, pause and let that sink in. Somewhere out there, in the silent black between stars, there could be entire worlds carrying alien oceans, unknown ecosystems, and possibilities we have not yet begun to imagine. Worlds with no sunrises, no sunsets, no constellations. Just endless night. And yet, against every instinct that tells us darkness means death, those worlds could still be alive. That is the haunting beauty of rogue planets. They remind us that the universe does not play by our rules. It plays by its own, and it is far more creative, far more generous with possibilities than we ever gave it credit for. Before we move on to the next topic, drop a quick comment and let us know where you're watching this from and what time it is for you. It's amazing how we're all connected, each of us chasing that perfect night's sleep. If this resonates with you, please like this video, subscribe to our channel Restwise, and join the journey. Ocean worlds, picture standing on a shoreline, but no matter where you walk, the ocean never ends. No continents, no islands, no mountains piercing the horizon, just water stretching in every direction forever. That is what an ocean world would be like. Entire planets covered not by land, but by global seas. And the wild thing is, scientists think these are not rare at all. In fact, ocean planets could outnumber Earth like rocky worlds across the galaxy. It almost feels like something out of mythology, a world where the only landscapes are waves, storms, and endless blue. But unlike myths, the science behind them is very real. Astronomers studying exoplanets have found worlds larger than Earth with densities suggesting thick layers of water. Not puddles, not shallow seas, but oceans hundreds of miles deep. For comparison, the deepest trench on Earth, the Mariana Trench, only cuts about 7 miles down. Imagine multiplying that by 50 by 100 and realizing there is still no seafloor in sight. And here is where it gets even more astonishing. Deep oceans like that create conditions unlike anything we can picture on Earth. The pressure at the bottom would be so crushing that water itself changes form. Under extreme pressure, water molecules lock into solid structures even at high temperatures, creating what scientists call exotic ice. It is not the kind of ice you drop into a drink. This stuff is so dense and alien that it forms layers between the liquid ocean and the rocky core of the planet. In other words, the floor of an ocean world is not rock. It is ice. Ice so strange we have never touched it, never seen it directly, but the math says it must exist. That sounds unlivable, right? An alien ocean sealed off by pressure and exotic ice. But then we look back at Earth, and something fascinating happens. Life here started in the ocean. Not on land, not in the sky, in water. And even today, the ocean is home to some of the most resilient, bizarre forms of life we know. Microbes live in boiling hot hydrothermal vents. Fish thrive in total darkness miles beneath the surface. Creatures withstand pressures that would crush a submarine like a soda can. If life can adapt to Earth's oceans in ways we never expected, why not in the endless oceans of another world? Think of Europa, one of Jupiter's moons, or Enceladus, one of Saturn's. Both are covered in ice, and beneath that ice lie oceans of liquid water. We have even seen plumes of water vapor spraying from Enceladus into space, carrying organic molecules. That is in our own solar system. Multiply that by billions of stars, and the odds of fully aquatic planets become almost certain. And here is the part that validates the wonder. Water is the universal solvent. It is the perfect medium for life because it allows chemicals to mix, collide, and form complex reactions. The fact that Earth life depends so heavily on it is not random chance. It is chemistry. So when we talk about ocean worlds, we are not just indulging in science fiction. We are following the chemistry that already built us. But imagine what life there would look like. Without land, evolution would have no reason to push creatures out of the water. There would be no forests, no deserts, no mountains. Just layers upon layers of marine ecosystems. Maybe life would cluster near volcanic vents in the deep. Maybe entire civilizations of alien creatures would move through endless currents, never knowing what a sky is. And the lack of land raises another question. Would intelligent life ever build technology without fire, without tools shaped from rock or metal? Maybe they would, in ways we cannot yet comprehend. Or maybe their intelligence would remain ocean-bound, vast and alien, forever drifting. The thought alone is both haunting and beautiful. Worlds where storms rage endlessly, where tsunamis roll unchecked, because there is no coastline to stop them, where lightning flashes across a sky that reflects only ocean beneath. Planets where every sunrise glimmers on nothing but waves, and every sunset vanishes beneath a horizon that never changes. And here is the tease that makes ocean worlds impossible to forget. These may be the most common type of habitable planet in the galaxy, not Earth, like with continents and cities, but water worlds, seas without end. So when we wonder if we are alone, we have to picture not aliens walking on land, but creatures swimming through endless oceans, thriving in a kind of paradise that covers an entire globe. A planet that is nothing but water sounds like fantasy. But the more we learn, the more it looks like reality. And somewhere out there, beyond our reach for now, whole worlds may be waiting, their waves rolling endlessly beneath alien skies. Super Earths. Think about how fragile Earth feels sometimes. Hurricanes, earthquakes, wildfires, ice ages in our past and climate change in our present. Now imagine a world like Earth, but bigger, more gravity to hold on to its atmosphere. More land, more oceans, more stability. That is what astronomers call a super Earth, and here is the mind-bending part. These might be the most common type of planet in the galaxy. Not tiny rocks like Mercury, not gas giants like Jupiter, but something right in the sweet spot, larger than Earth, smaller than Neptune, and potentially better at supporting life than our own planet. At first that sounds like wishful thinking, like we are just projecting our hopes onto alien worlds, but the shocker is, the physics makes sense. Take gravity. Earth is just massive enough to hold its atmosphere, but only barely. Over billions of years, we have lost lighter gases like hydrogen and helium. A super Earth, with maybe twice or 3 times Earth's mass, would have stronger gravity. That means thicker air, a more stable climate, and protection against cosmic rays. It might even keep its oceans for longer, preventing them from slowly evaporating into space. In other words, A super Earth is like Earth with upgrades. Now here is where it really challenges our imagination. These worlds could have mountains taller than Everest, oceans deeper than anything we know, and skies richer with clouds. And because of their size, tectonic activity might be more consistent, recycling carbon and balancing climate in ways that keep the surface habitable for billions of years, longer than Earth can manage. Some scientists think that life on a super Earth would not only be possible, it might actually have a better shot at thriving than it does here. This is where we bring it back to something we already know. Earth itself has almost been too unstable at times. It has gone through mass extinctions, meteor strikes, and ice sheets that once covered continents. Yet life survived and adapted. Now imagine giving life more favorable odds. A thicker atmosphere to shield from radiation. More gravity to hold on to water. A planet that stays in its habitable zone longer than Earth's 4.5 billion years. That does not just make life possible. It makes advanced life more likely. But there is a catch that makes these worlds even more fascinating. A stronger pull of gravity also means a heavier weight on anything living there. If Earth gravity is 1 g, a super Earth might be 1.5 g, maybe even 2 g. That means if you weigh 150 pounds here, you would feel like 300 there. Imagine how that would shape life. Creatures might grow stockier, sturdier, built to withstand pressure. Wings might be harder to evolve because flight would take more energy. Maybe intelligence would emerge in beings who are shorter and more muscular, moving slowly but built like living fortresses. The very gravity of a super Earth would sculpt evolution into forms we can barely picture. And think about how we would experience it. If you stood on the surface of a super Earth, your legs would feel heavier, your chest would rise and fall with effort, but the view around you might be breathtaking. A sky with richer blues, maybe forests that grow thicker, because the air is denser and plants can spread nutrients more efficiently. Maybe oceans that shimmer under a stronger atmosphere, holding storms that last longer but balance global temperatures with incredible precision. It would feel both familiar and utterly alien. Here is what validates the excitement. When astronomers scan the galaxy, super Earths show up everywhere. They are among the most frequently detected exoplanets. Kepler, the telescope that revolutionized our knowledge of other worlds, found them again and again, which is ironic because we do not even have one in our own solar system. Mercury, Venus, Earth, Mars, none of them qualify. It is as if we are the odd ones out, the anomaly. Meanwhile, the universe seems to be filled with planets that are Earth's bigger, more stable cousins. And here comes the tease that makes this impossible to stop thinking about. If super Earths are common, and if they really do offer more stability, stronger atmospheres, and longer lifespans for habitability, then the most likely place for alien civilizations may not be planets like ours. They may live on worlds that are in every measurable way superior to Earth. Maybe we are not the peak of cosmic luck. Maybe we are living on hard mode, while somewhere out there, civilizations flourish on planets that give life every advantage it could ask for. That thought cuts both ways. On one hand, it is humbling. Earth feels special to us because it is all we know, but the universe may be littered with worlds that put ours to shame. On the other hand, it is inspiring. If life can make it here through every disaster, think what it could become on a world designed by physics itself to be more stable. Super Earths do not just expand our imagination of what is possible. They suggest that life is not fragile, not rare, not hanging by a thread. It may be thriving, right now, under alien skies on worlds far stronger and more generous than the one we call home. Tidally locked planets. Imagine living on a planet where the sun never moves. If you looked up, it would hang in the same spot in the sky, never setting, never rising. For half the planet, that sun would blaze overhead forever, baking the land in eternal daylight. And for the other half, there would be nothing but endless night, a frozen wasteland trapped in permanent darkness. This is the strange reality of tidally locked planets. The shocking part is how common they might be. Most of the stars in our galaxy are red dwarfs, smaller and cooler than our sun. Planets orbiting close to them can still sit in the habitable zone, where liquid water could exist. But being so close comes with a side effect. Their gravity locks the planet's rotation, just like our moon is locked to us. The result is one side always facing the star, the other side forever turned away. What sounds like a bizarre, alien scenario is actually probably one of the most frequent arrangements of planets in the entire universe. At first glance, it feels like a death sentence for life. How could anything survive on a planet split between burning heat and frozen dark? The day side could be a desert hotter than boiling point, while the night side could be a sheet of ice cold enough to shatter steel. It seems like one half would be roasted, and the other half frozen solid. But here is where it gets fascinating. Climate models suggest that with a thick enough atmosphere, heat from the day side could circulate to the night side. That means instead of total extremes, the planet could have a livable strip running along the twilight zone, a permanent ring of eternal dusk where conditions might actually be just right for life. Think about how strange that would feel. Standing in that twilight belt, you would see the sun fixed on the horizon, never moving. It would not rise, it would not set. It would just glow forever, painting the sky in an endless sunset. The shadows would never change. Plants, if they existed, would evolve in a world with no seasons and no true night, and creatures might adapt to the steady balance of half-light, never knowing the rhythm of day and night that defines life on Earth. Now let's validate the idea with what we already know. On Earth, life has proven it can thrive in extreme conditions. Microbes live in the frozen ice sheets of Antarctica and in boiling hot springs. Deep sea creatures live in darkness so complete they have never seen sunlight. If life can adapt here, it is not hard to imagine it adapting to the permanent extremes of a tidally locked world. On the scorching side, maybe organisms develop heat-resistant shells or live underground where temperatures are cooler. On the frozen side, maybe they cluster near volcanic vents, feeding on geothermal warmth, and in the twilight belt, maybe entire ecosystems bloom, nourished by the balance of eternal dusk. Think about the psychology of living there. Humans are tied to cycles. We sleep when it is dark, we wake when it is light. But on a tidally locked world, there would be no natural rhythm. Time itself would feel different. Would people divide days artificially, just to stay sane? Or would they live in constant twilight, letting their bodies adapt to a timeless existence? It is a haunting thought, that whole civilizations could grow up never seeing a sunrise or a sunset, never looking at the stars, just existing in a world where the sky never changes. And here comes the tease that makes these planets unforgettable. If tidally locked worlds are the most common type of habitable planets around red dwarfs, then they may be the best places to actually find alien life. Forget the Earth clones we keep imagining. The first evidence of life we detect out there may come from a world where one half bakes forever, one half freezes forever, and all the magic of survival happens in the narrow band in between. Picture that thin strip from space, a glowing line wrapped around the middle of the planet, separating day from night. On one side, fire. On the other, ice. And in between, a belt of possibility where rivers flow, forests might grow, and creatures could thrive in a never-ending twilight. It is unsettling, but it is also beautiful. Tidally locked planets force us to realize that what seems unlivable to us may be the perfect stage for life somewhere else. And if civilizations exist there, they would not just live differently. They would think differently, dream differently, build their entire sense of time and meaning in ways we cannot even imagine. A world of endless day, endless night, and eternal dusk. It sounds like something out of a myth. But in truth, it may be one of the most ordinary realities in the universe. Lava worlds. Imagine standing on a planet where the ground beneath you glows red, rivers of molten rock carving paths across the surface, and the air itself shimmering with heat. No oceans, no forests, no fields. Just a world alive with fire. These are lava planets, places where the surface is made not of soil and stone but of endless magma. The shocking part is they are not just theoretical. We have actually found candidates for these fiery worlds. Take 55 Cancri E, a planet about 40 light-years away. It is so close to its star that a year there lasts less than 18 hours. Astronomers believe its surface is a sea of molten rock, reshaping itself constantly, glowing like a furnace. Imagine a planet that never cools, where the very idea of solid ground does not exist. That is not science fiction, that is data. And it makes sense once you think about it. When planets form, they start as molten spheres, hammered by collisions and heated from within by radioactive decay. Earth itself was once a lava world. Over time it cooled, hardened, and gave rise to continents and oceans. But some planets never get that far. Some orbit so close to their stars that they remain trapped in eternal heat, their surfaces locked in a state of constant eruption. On these worlds, lava lakes bubble the size of continents. Volcanic fountains spray higher than skyscrapers. Even the atmosphere could be thick with vaporized rock and metal, raining down minerals as molten droplets. It sounds like the ultimate hellscape, a place where no human could walk for even a second. Temperatures high enough to melt steel. Skies filled with choking ash and boiling gases. From our perspective, it looks like pure destruction. But here is the twist. Lava worlds are important. They show us the earliest stage of planetary evolution, a snapshot of what young Earth once looked like. Studying them is like traveling back in time to see the fiery chaos that eventually shaped the cradle of life. And here is where it connects to something familiar. Volcanism on Earth has always been both destructive and creative. The eruption of Mount Vesuvius buried Pompeii, but volcanic soils are among the most fertile in the world. Entire ecosystems depend on minerals that volcanoes release. Lava builds new islands, reshapes coastlines, and recycles the Earth's crust. Without volcanism, Earth might never have developed the balance of land, water, and atmosphere that makes life possible. So when we look at lava worlds, we are not just seeing doom. We are seeing raw creation in its most violent form. Now imagine evolution trying to survive there. On Earth, extremophiles, organisms that thrive in boiling hot springs or near underwater volcanic vents, already exist. They live in conditions that seem impossible, using heat and chemicals as fuel. On a lava world, it is not impossible to imagine life forms adapted to heat far beyond what we can tolerate. Maybe they live underground, shielded from the worst of the heat. Maybe they metabolize minerals instead of water. It sounds outrageous, but then again, life has already surprised us countless times. And think about the view from orbit. A lava planet would not look like the calm blue marble we know. It would blaze. The surface would glow red and orange, constantly shifting, with bright scars of molten rivers stretching for thousands of miles. Storms of ash could rise into the atmosphere and circle the planet like permanent scars. To see it would be like watching a world on fire, alive in a way both terrifying and mesmerizing. Here is the tease that makes these planets impossible to ignore. Lava worlds may be the stepping stones of habitability. They begin as fiery furnaces, but over billions of years they can cool, harden, and transform into stable worlds capable of supporting life. Earth itself proves that path is real. So when we see lava planets today, we might not just be looking at dead rocks. We might be looking at the early chapters of alien Earths, planets that will one day host oceans, continents, and maybe even life. There is something haunting in that. A planet covered in fire looks like the very definition of death, yet it may simply be the beginning of something much greater. The violence is not the end of the story. It is the first act. Somewhere out there, entire worlds are burning right now, not as a finale, but as the opening scene in the long play of creation. Pulsar Planets, a planet orbiting not a shining sun, but the corpse of a star. Instead of warm golden light, its sky is dominated by the relentless flash of radiation pulses, like a cosmic lighthouse sweeping across the void. These are pulsar planets, worlds that circle dead stars, stars that have already gone through their violent collapse. The very idea feels impossible. How could a planet survive after its sun dies in a catastrophic supernova? And yet they exist. Here is the shocker. The very first confirmed exoplanets ever discovered were not around a bright young star. They were around a pulsar. Back in the 1990s, astronomers detected tiny regular shifts in the pulses of a neutron star called PSR B12 2057+12. Those shifts revealed planets tugging at it with their gravity. Imagine that. The first alien worlds humanity ever found were circling the burned out remains of a dead sun. That alone rewrote everything we thought we knew about what was possible. To understand how bizarre this is, you need to picture what a pulsar really is. When a massive star runs out of fuel, it explodes in a supernova, shedding its outer layers in a flash brighter than an entire galaxy. What remains is a core so dense that atoms are crushed into neutrons. A pulsar is that neutron star spinning at incredible speeds, firing beams of radiation out of its magnetic poles. Some spin hundreds of times per second, with a precision so sharp that they keep time better than atomic clocks, orbiting something that extreme should be impossible for planets. And yet, somehow, there they are. And here is where it gets even more mind-bending. No one is entirely sure how pulsar planets form. Some might be survivors, battered remnants of the original solar system that somehow avoided annihilation. Others might form afterward, from the debris left swirling around the dead star. That means, in a way, they are planets born from death. Second, generation worlds forged out of chaos. If Earth were to be obliterated and reborn after the sun's death, that is what it might look like. Now let's bring this back to what we know. Life on Earth depends on stable sunlight, on radiation levels that do not instantly fry DNA. Pulsars, on the other hand, bathe their planets in lethal radiation. Any surface exposed to those pulses would be scorched beyond recognition. But just because the surface seems hostile does not automatically mean life is impossible. Life on Earth has adapted to radiation in surprising ways. There are microbes called radiodurans that can withstand doses of radiation 1,000 times greater than what would kill a human. Some even repair their DNA after being shredded. If such resilience is possible here, then who is to say it could not evolve in even harsher conditions around a pulsar planet? Maybe life would retreat underground or beneath oceans, shielded from the deadly blasts above. Imagine standing there for a moment. The ground beneath your feet is scorched rock, maybe coated with strange metallic dust. Above, the sky flickers rhythmically as the pulsar spins, a constant reminder that your sun is not alive but dead, still dictating the rhythm of your days with its cosmic heartbeat. Time itself would feel different, chopped into fractions of seconds by the flashing of the star. It would be alien in every possible way, and yet still a world orbiting like any other. And here is why pulsar planets matter to us. They force us to question our assumptions about where planets, and maybe even life, can exist. If planets can form and orbit around stars that are long dead, then planets are far more resilient, far more stubborn than we ever imagined. The universe does not waste material. It recycles it, reshapes it, and builds again, even out of destruction. Now for the tease that lingers long after you hear it. If the very first exoplanets we ever found were orbiting a pulsar, what does that say about the rest of the galaxy? It suggests that planets may be everywhere. Around newborn stars, aging stars, even stars that have already died. And if planets are that common, then life has had billions upon billions of chances to take root in places we once dismissed as impossible. A pulsar planet is a symbol of survival, a reminder that even after death, even after collapse and chaos, new worlds can emerge. They may not look welcoming, but their existence tells us that the universe is endlessly creative, endlessly persistent. Out there in the darkness, circling dead stars, are worlds that should not exist, and yet they do. Methane worlds. Not every ocean in the universe is made of water. Picture standing on the shore of a vast lake, waves lapping against the edges, mist rising into the air. But instead of water, the liquid is methane, a substance that on Earth is a flammable gas. You could strike a match in that atmosphere and nothing would happen, because the air itself would lack the oxygen needed to ignite it. That is what a methane world offers. A place where entire seas are made of liquid hydrocarbons, where alien chemistry rewrites the rules of what an ocean even is. Here is the shocking part. We do not have to look across the galaxy to imagine this. We already know of one such place in our own solar system. Saturn's moon Titan is covered in lakes and seas of liquid methane and ethane. Its atmosphere is thick, orange, and hazy, and it rains methane the way it rains water on Earth. Imagine standing there, watching drops of liquid methane fall from the sky, pooling into rivers that snake into massive seas larger than the Great Lakes combined. That is not science fiction. That is real. And Titan is just the beginning. If it can exist here, orbiting in the cold outskirts of our solar system, then methane worlds could be common across the galaxy. Planets and moons colder than Earth could host entire methane cycles, with evaporation, rain, rivers, and oceans. A mirror image of Earth's water cycle, but with entirely different chemistry. Instead of beaches of sand, you might find shores of frozen hydrocarbons. Instead of clouds of water vapor, you would see smoggy skies filled with methane droplets. Now, here is where the validation kicks in. Life on Earth depends on water, But what if water is not the only solvent capable of supporting biology? Chemists have long pointed out that methane, though less versatile than water, can still act as a medium for chemical reactions. In fact, a study showed that cell-like structures called azotosomes could theoretically form in liquid methane. That means that on a world like Titan, alien life might not only be possible, it might be based on an entirely different set of building blocks than ours. Imagine life not as we know it, but as a true alternative form of biology. Breathing gases we would choke on, drinking liquids that would freeze our blood solid. And let's tie it back to Earth. We often assume water is universal because it is what we know. But even here, we see life pushing boundaries. Microbes live in acid pools, in salty brines, in toxic waste dumps. They adapt to whatever liquid environment exists. So why should life elsewhere be limited to water? If chemistry allows it, evolution will try it. Methane seas may look alien to us, but to the creatures of those worlds, they would feel as natural as our oceans feel to whales and dolphins. Think about what it would feel like to stand on the edge of one of those alien seas. The sky dim and hazy, the air thick and cold. Waves moving slowly under the pull of gravity weaker than Earth's. No smell of salt, no sound of crashing surf, just the strange quiet of a liquid that does not behave quite like water. You might scoop some into your hands and watch it drip through your fingers, knowing that on your own planet this substance is explosive, yet here it is calm, natural, and life-sustaining. It would be one of the most surreal experiences imaginable. And here is the tease that makes Methane Worlds impossible to forget. If they exist in abundance, and the evidence suggests they might, then life in the universe might not just look different, it might run on a completely separate set of rules. We tend to search for Earth like worlds with water and oxygen and sunlight. But maybe the universe is filled with thriving ecosystems built on methane, where creatures swim in cold alien seas and breathe in gases that would poison us instantly. Maybe water-based life like ours is just one chapter in a much bigger book of possibilities. The idea is unsettling because it forces us to admit that we might not recognize life, even if it was right in front of us. But it is also exhilarating. It means the cosmos is not limited to repeating Earth's formula. It is endlessly creative, endlessly experimental. Somewhere out there are planets with black seas of liquid methane, under orange skies, carrying life so strange that it would redefine what the very word life even means. Exoplanets with glass rain and metal clouds. Imagine looking up at a stormy sky, expecting rain, but instead of water, shards of glass fall sideways in the wind. Imagine clouds, not made of vapor, but of vaporized metal, drifting like molten mirrors across the atmosphere. These are not special effects from a science fiction movie. These are real conditions on some of the strangest exoplanets we have discovered. Here is the shocking reality. Astronomers have found planets so close to their stars that their atmospheres are superheated to thousands of degrees. At those temperatures, rock, iron, and even gems can vaporize into the sky. On one such planet, called HD 189733b, the winds blow at over 4,000 miles per hour, carrying particles of glass sideways across the atmosphere. Not falling gently like rain, but whipping horizontally at speeds that would shred anything in their path. Another planet, MIS 121b, has clouds of vaporized metals like iron and magnesium, condensing and raining molten droplets. These are not gentle weather systems. They are violent alien storms unlike anything we could imagine living through. And yet, when you think about it, it makes sense. Weather is simply the atmosphere responding to energy. On Earth, sunlight warms oceans and air, creating cycles of evaporation, condensation, and rain. On a world far hotter than Earth, those same processes still occur, only with different ingredients. Instead of water rising into clouds, it is metals. Instead of rain, it is molten iron. Instead of hail, it is shards of glass. The physics is the same. The chemistry is different, and that difference transforms a familiar thing into something terrifyingly alien. Now let's validate how this connects back to Earth. We already know that elements behave differently under extreme conditions. Volcanic eruptions here produce ash plumes that darken skies. Lightning storms create hailstones the size of baseballs. Even on our planet, weather can feel apocalyptic. Scale that up to an environment with temperatures hot enough to melt rock, and suddenly, glass rain and metal clouds are not only possible, they are inevitable. The laws of physics do not stop at Earth's edge. They just play out with new materials. And here is where it gets truly fascinating. For us, rain is part of the water cycle. It nurtures plants, fills rivers, and sustains life. On a glass rain world, weather would not nurture anything. It would be pure destruction. Imagine trying to walk across the surface of such a planet. Every gust of wind cutting through armor, every droplet of rain capable of melting metal. For us, it would be instant death. But what if, for something else, that environment is normal? What if life evolved to see molten iron rain not as a hazard, but as part of the natural rhythm of existence? It sounds impossible, but Earth's own history gives us reasons to hesitate before ruling it out. Extremophiles survive in boiling acid pools, in radioactive waste, in liquid asphalt. Creatures like the water bear can survive the vacuum of space and lethal radiation. Life adapts. It always has. So when we picture glass rain or metal clouds, maybe we should not see only destruction. Maybe we should see a different kind of ecosystem, one tuned to extremes that would obliterate us but sustain something else entirely. Close your eyes and imagine the view from orbit. A planet glowing blue from scattered light, streaked with violent storms. The clouds shimmer metallic, flashing like liquid silver under a blazing sun. From above, it would look beautiful, even mesmerizing. But beneath those clouds, glass and molten metal rain sideways across a surface we could never step foot on. A paradise to the eye, a nightmare to the body. And here is the tease that lingers. The more we study exoplanets, the stranger they become. We went looking for other Earths, and instead we found worlds with sapphire-colored skies, molten iron storms, and glass falling sideways in hurricane winds. These discoveries remind us that the universe is not obligated to look familiar. It is far more creative than that. So when we talk about life beyond Earth, we cannot limit our imagination to green valleys and blue oceans. Out there somewhere it might be raining glass. It might be storming molten iron. And just maybe, under those alien skies, life is not only surviving but thriving in ways we have yet to dream. Ultra-hot Jupiters. Think about Jupiter for a moment. Massive, stormy, striped with clouds, but still cold and far from the sun. Now flip that image upside down. Imagine a gas giant not drifting in the outer reaches of a system, but hugging so close to its star that it orbits in just a day or two. Its atmosphere blasted by heat so intense that molecules themselves rip apart. This is an ultra-hot Jupiter, a planet so scorched that even our concept of weather falls apart. Here is the shocker. These are real. We have found them, and they defy every expectation of what gas giants should be. On some ultra-hot Jupiters, Temperatures soar above 3,000 degrees Celsius, hotter than the surface of some stars. At that heat, hydrogen molecules split apart, only to recombine on the cooler night side, creating a constant chemical cycle of destruction and rebirth. Metals like iron and titanium do not sit locked in the ground. They vaporize into the skies, forming metallic clouds that can rain molten droplets. If you could somehow fly there, you would not find a planet, you would find a furnace. And it gets even stranger. Ultra-hot Jupiters are tidally locked, meaning one side always faces the star. That day side is permanently blasted, hotter than molten lava. The night side, though still scorching by our standards, is cooler, creating a temperature difference so extreme that supersonic winds scream across the atmosphere to balance it. These winds can whip faster than the speed of sound, carrying vaporized metals and scattering heat around the globe in an endless, violent circulation. The very sky is alive with chaos. It sounds like a cosmic horror story, but it also makes perfect sense. When we first started finding exoplanets, astronomers were stunned to see gas giants orbiting so close to their stars. They expected worlds like Jupiter to be far out, like in our own solar system. But instead, we found hot Jupiters, parked right next to their stars, and among them, the most extreme, the ultra-hot Jupiters. They do not match our model, but they force us to expand it. That is the universe reminding us that our solar system is not the template. It is just one version. And here is where we validate the importance. These planets are laboratories of physics at its most extreme. By studying them, scientists test how atmospheres behave under conditions we cannot replicate on Earth. We learn how radiation interacts with molecules, how winds redistribute heat, and even how planets can evolve under crushing stellar forces. Every measurement pushes our models of climate and chemistry further, and those same models help us when we turn our telescopes towards smaller, potentially habitable worlds. Ultra-hot Jupiters may look like death, but they are teaching us about life. Now imagine the view up close. You are in orbit, staring down at a gas giant glowing from its own heat. Clouds shimmer metallic, storms rage at unimaginable speeds, and the star dominates the sky, so close it fills half the horizon. On the day side, the planet's atmosphere is nearly transparent because molecules have broken apart under the heat. On the night side, those molecules reform, glowing faintly, like the entire world is breathing in sync with the star. It is both terrifying and mesmerizing, a planet that feels more alive than dead, but alive in fire. And here comes the tease. Ultra-hot Jupiters are only the beginning of what we will find. If planets like these exist, giants so close to their stars they are practically inside them, then what other extremes are out there? Worlds made of carbon, shining with diamond crusts, worlds of pure ice orbiting dying stars. The universe does not just allow extremes, it specializes in them. And every time we think we have found the strangest world possible, something new appears that is even stranger. Ultra-hot Jupiters may never host life. They are too violent, too unstable, too scorched. But their existence tells us something profound. Planets can survive conditions that seem unimaginable. They can orbit where no planet should orbit. They can weather storms that break our models of physics. And if planets can do that, then life, stubborn, adaptive, and unpredictable, may find ways to exist in places we have not yet dared to imagine. These are not just scorched giants. They are cosmic reminders that the universe is wilder, hotter, and more inventive than our imaginations are ready for. Ice planets. Close your eyes and picture a planet where silence reigns. No waves crashing, no leaves rustling, no rain falling. Just wind sweeping across endless plains of ice. A world where every mountain is frozen solid, every ocean buried under miles of permafrost, and the ground itself creaks with cold. These are ice planets. Entire Earth, like worlds gripped in permanent deep freeze. Here is the shocker. Ice planets may not be rare at all. In fact, they could be some of the most common planets in the universe. Stars are often faint, smaller than our Sun, and many planets orbit too far from their warmth. Without enough energy to melt surface water, they become snowball worlds locked in glaciers that never thaw. Some may have frozen thousands of years ago. Others may have been born that way, never knowing a liquid ocean at the surface. And yet, just because they look lifeless does not mean they are. Think about what happens when water freezes. It expands and forms a crust, but beneath that crust, heat from the planet's core can still flow upward. We see this in our own solar system. Europa, Ganymede, and Enceladus, moons locked in ice, all likely hide liquid oceans below. On Enceladus, geysers of water burst through cracks in the ice, spraying organic molecules into space. That means even a planet completely frozen on the surface could hold vast oceans underneath, kept liquid by geothermal heat. What looks dead on the outside may be thriving below it. And here is the validating part, because Earth itself has been here before. Hundreds of millions of years ago, our planet went through what scientists call snowball Earth periods. Ice sheets stretched all the way to the equator, freezing nearly the entire surface. Yet life survived. Microbes found refuge in cracks of ice, near volcanic vents, and deep in the ocean. When the ice finally melted, life rebounded stronger than before. That history proves something important. Frozen does not mean dead. It means waiting. Now imagine standing on the surface of one of these frozen exo-Earths. The horizon would be blinding white, the sun dim and distant, barely more than a pale disk in the sky. You would hear the groan of shifting glaciers, the crack of ice as temperatures rise and fall. No rivers, no forests, no green at all. Just a desert of frost stretching into infinity. But dig below the surface, and you might find liquid oceans with entire ecosystems hidden from view. Creatures that never see starlight. Ecosystems that have no seasons, no day or night, just a constant cold stability stretching on for millions of years. And here is a thought that challenges our imagination. What if intelligent life arose on an ice planet, not on the surface, but beneath it? They would never look at the stars. Their entire universe would be a subterranean ocean. They would map currents instead of constellations. They would tell stories not of the sky, but of the heat vents that sustain them. To them, the cosmos would be invisible, unreachable, and yet they would still be alive, still building meaning in the shadows of their frozen world. Bring it back to science for a moment. Astronomers already suspect that subsurface oceans may be more common than surface oceans across the galaxy. Water beneath ice is protected from radiation, shielded from meteor strikes, and stable for billions of years. That makes ice planets not barren wastelands, but some of the most promising places to look for life. The very conditions that look hostile to us could be perfect incubators for alien biology. And now the tease. If ice planets are as common as scientists believe, then the universe could be filled with hidden oceans and secret biospheres, locked away beneath frozen crusts. The next discovery of life may not come from a warm, Earth-like world with blue skies. It may come from a place that looks dead from the outside but is bursting with life below. That thought changes everything. Frozen worlds remind us that appearances are deceiving. They look silent, empty, sterile, but beneath their frozen shells may be stories still unfolding, stories of survival, patience, and possibility. Somewhere out there, under endless fields of ice, entire alien oceans may already be alive, waiting for the day we finally break through the crust and listen. Planets with highly elliptical orbits. On one side of the year, your planet is a frozen wasteland, locked in ice, oceans sealed under sheets of frost, and every breath of wind stings like knives. But then, as the months pass, the same planet swings closer to its star, and suddenly the world is scorching. Glaciers collapse, rivers boil, and deserts spread across what used to be frozen plains. This is the reality of a planet with a highly elliptical orbit, a world that does not circle its star in a neat, steady loop, but instead stretches out into a cosmic oval, dragging its climate into chaos. And here's the shocker. Planets like this are not rare oddities. Astronomers have already detected multiple exoplanets with orbits so eccentric they make our solar system look boring. Take HD 8606b, a gas giant whose orbit is one of the most extreme we have ever measured. Most of the time it drifts far from its star, cold and dark, but every 111 days it dives close, heating up by hundreds of degrees in just hours. Imagine living on a planet like that. One season that feels like deep space winter, and another that feels like standing inside a furnace. And remember, these are not short seasons. If Earth had such an orbit, entire generations could be born in winter and never see summer, while their descendants would live through a burning age with no trace of ice. Seasons would not just be a background shift. They would define history, culture, even survival. Imagine civilizations rising during warm phases, only to collapse as the planet swings back into ice ages. Imagine myths and religions forming around the return of heat or the return of cold, entire worldviews shaped by a cycle no one can escape. Here is where it gets fascinating. On Earth, seasons are caused by the tilt of our axis, not our orbit. Our path around the sun is nearly circular, so our distance barely changes. That stability is one reason life here has had time to flourish. But on a planet with a stretched orbit, distance changes everything. When the planet is close to the star, it can be drenched in radiation, even losing part of its atmosphere to the heat. When it is far, it can plunge into global freeze. The ecosystem would have to endure endless cycles of feast and famine, growth and extinction. Survival would not mean adapting once. It would mean adapting endlessly. And yet, here comes the validation. Life on Earth has already proven it can adapt to cycles, even extreme ones. During the ice ages, animals grew thicker fur, humans built fire and shelters, and entire species migrated with the seasons. In hot, dry periods, plants evolved ways to store water, and animals learned to burrow underground. If life here can bend to ice and fire, who is to say life elsewhere could not do the same, only on a grander scale? Maybe evolution on an elliptical planet happens faster, because survival is always urgent. Maybe intelligence there is born not out of comfort, but out of constant struggle. Now picture the sky from such a world. During the cold phase, the star would be tiny and weak, barely visible through the haze of frost. The horizon would glow with auroras faint and slow, as if the world itself is asleep. Then, as the planet swings inward, the star would grow blinding, dominating the sky, scorching the land. Storms would ignite, seas would evaporate, lightning would dance across continents. The same sky that once promised nothing but ice would now be an engine of fire. That duality would shape not just survival, but imagination. Every child growing up there would know that their world has two faces. And here is the tease. If planets with elliptical orbits are out there, then so are civilizations that may live through centuries of ice followed by centuries of fire. Their art, their myths, their technologies would be shaped by extremes we can barely conceive. Maybe they build underground cities to endure both. Maybe they learn to migrate globally, following habitable zones as they shift. Or maybe they dream of escaping their orbit entirely, of breaking free from the cosmic leash that keeps pulling them between heaven and hell. Highly elliptical planets remind us of something profound. Stability, like we have on Earth, is not the default, it is a gift. Most worlds out there may be ruled by extremes, by seasons so harsh that life must claw for every chance it gets. And yet, if life can rise in those places, it would not just endure. It would be tempered like steel, forged in cycles of ice and fire, carrying resilience that makes our own survival look easy. These are not just planets with odd orbits. They are worlds where time itself feels like an enemy, and yet also the very force that might give birth to life. Worlds of extreme seasons that never let their inhabitants rest. Planets with highly elliptical orbits. On one side of the year, your planet is a frozen wasteland, locked in ice, oceans sealed under sheets of frost, and every breath of wind stings like knives. But then, as the months pass, the same planet swings closer to its star, and suddenly the world is scorching. Glaciers collapse, rivers boil, and deserts spread across what used to be frozen plains. This is the reality of a planet with a highly elliptical orbit, a world that does not circle its star in a neat, steady loop, but instead stretches out into a cosmic oval, dragging its climate into chaos. And here's the shocker. Planets like this are not rare oddities. Astronomers have already detected multiple exoplanets with orbits so eccentric they make our solar system look boring. Take HD 8606b, a gas giant whose orbit is one of the most extreme we have ever measured. Most of the time it drifts far from its star, cold and dark, but every 111 days it dives close, heating up by hundreds of degrees in just hours. Imagine living on a planet like that. One season that feels like deep space winter, and another that feels like standing inside a furnace. And remember, these are not short seasons. If Earth had such an orbit, entire generations could be born in winter and never see summer, while their descendants would live through a burning age with no trace of ice. Seasons would not just be a background shift. They would define history, culture, even survival. Imagine civilizations rising during warm phases, only to collapse as the planet swings back into ice ages. Imagine myths and religions forming around the return of heat or the return of cold, entire worldviews shaped by a cycle no one can escape. Here is where it gets fascinating. On Earth, seasons are caused by the tilt of our axis, not our orbit. Our path around the sun is nearly circular, so our distance barely changes. That stability is one reason life here has had time to flourish. But on a planet with a stretched orbit, distance changes everything. When the planet is close to the star, it can be drenched in radiation, even losing part of its atmosphere to the heat. When it is far, it can plunge into global freeze. The ecosystem would have to endure endless cycles of feast and famine, growth and extinction. Survival would not mean adapting once. It would mean adapting endlessly, and yet, here comes the validation. Life on Earth has already proven it can adapt to cycles, even extreme ones. During the ice ages, animals grew thicker fur, humans built fire and shelters, and entire species migrated with the seasons. In hot, dry periods, Plants evolved ways to store water, and animals learned to burrow underground. If life here can bend to ice and fire, who is to say life elsewhere could not do the same, only on a grander scale? Maybe evolution on an elliptical planet happens faster, because survival is always urgent. Maybe intelligence there is born not out of comfort, but out of constant struggle. Now picture the sky from such a world. During the cold phase, the star would be tiny and weak, barely visible through the haze of frost. The horizon would glow with auroras faint and slow, as if the world itself is asleep. Then, as the planet swings inward, the star would grow blinding, dominating the sky, scorching the land. Storms would ignite, seas would evaporate, lightning would dance across continents. The same sky that once promised nothing but ice would now be an engine of fire. That duality would shape not just survival, but imagination. Every child growing up there would know that their world has two faces. And here is the tease. If planets with elliptical orbits are out there, then so are civilizations that may live through centuries of ice followed by centuries of fire. Their art, their myths, their technologies would be shaped by extremes we can barely conceive. Maybe they build underground cities to endure both. Maybe they learn to migrate globally, following habitable zones as they shift. Or maybe they dream of escaping their orbit entirely, of breaking free from the cosmic leash that keeps pulling them between heaven and hell. Highly elliptical planets remind us of something profound. Stability, like we have on Earth, is not the default, it is a gift. Most worlds out there may be ruled by extremes, by seasons so harsh that life must claw for every chance it gets. And yet, if life can rise in those places, it would not just endure. It would be tempered like steel, forged in cycles of ice and fire, carrying resilience that makes our own survival look easy. These are not just planets with odd orbits. They are worlds where time itself feels like an enemy, and yet also the very force that might give birth to life. Worlds of extreme seasons that never let their inhabitants rest. Desert worlds. Imagine standing on a planet where the horizon stretches endlessly, but there is nothing to see except sand, rock, and sky. No rivers winding through valleys, no oceans glittering in the sunlight, no forests breaking up the view. Just dry, cracked land that has not seen a drop of rain for centuries. The air is thin, the heat during the day feels like a furnace, and the nights are so cold they bite into your skin. This is a desert world, a planet almost entirely devoid of water. Now here comes the shock. As empty as these places sound, desert planets might actually be more common than Earth, like worlds. Water is fragile on a cosmic scale. Too much heat, and it escapes into space. Too little atmosphere, and it cannot stay liquid. Too much distance from a star, and it freezes. Finding a world with balanced oceans and stable climates, like Earth, may be rare. But finding a dry, rocky planet where water has vanished or never formed in the first place, that could be the norm. In other words, the universe may be filled with deserts. And yet, do not mistake them for being simple or lifeless. Mars itself is a desert world, a place with no seas, no rivers left flowing. But we know it once had them. We can see the scars of dried-up deltas and lake beds. That means a desert world does not always start dry. Some of them may be ancient worlds that lost their oceans over billions of years. The tragedy is that they may have once been alive, only to slowly wither as their water evaporated into space. Imagine entire ecosystems erased, leaving only a barren husk of what once was. That is the hidden sadness of desert planets. But here comes the validation, because desert worlds might still carry possibilities. Life on Earth has found ways to thrive in our driest regions. In the Atacama Desert of Chile, some microbes survive without rainfall for decades, drawing what little moisture they need directly from the air. In Antarctica's dry valleys, life clings to rocks, protected from the brutal cold and wind. If Earth can sustain life in places that are practically waterless, then an entire planet designed as a desert might not be as hopeless as it looks. Maybe life there evolves not to swim or drink, but to conserve, to endure, to survive on a drop where we would need a river. And picture what such a world would feel like if you lived there. The culture of its people, if they existed, would be defined entirely by scarcity. Every grain of water would be sacred. Entire societies might form around the control of wells or underground aquifers. Rituals could emerge around dew, rain, or ice, because those events would be rare miracles. Instead of oceans, their myths would be about mirages. Instead of forests, their legends would describe endless dunes as living, moving entities. Just as humans on Earth have told stories shaped by the landscapes we inhabit, desert dwellers on another world would carry narratives born of dust and thirst. Now think of the skies on such a planet. Without much water in the atmosphere, clouds would be rare. That means the stars would blaze brilliantly at night, sharper and clearer than any sky on Earth. The days would be piercing, the sun burning without mercy, while the nights would chill under that same empty atmosphere. The duality would be harsh, but beautiful. An endless cycle of fire and frost, ruled by the silence of a world that holds nothing back. And here's the tease. If desert planets are as common as scientists believe, then searching for life may mean searching for the rarest signs. Not vast oceans, but tiny pockets of underground water, sheltered caves, or thin films of moisture clinging to rocks. It may mean that the first alien microbes we ever detect do not come from a lush green planet, but from a dry and nearly dead one, the kind of place we would dismiss at first glance as hopeless, only to discover it was hiding secrets under the dust. Desert worlds remind us of something humbling. Life does not always need abundance. It does not always need comfort. Sometimes it just needs a crack, a shadow, a chance to hold on. What looks barren to us might be a home for something unimaginable. And if we ever stand on a desert planet under its naked sky, we may realize that even in the emptiest places, the universe still finds a way to whisper that life is possible. Diamond planets. Imagine walking across a world where the ground beneath your feet is not stone or sand, but solid diamond. The mountains sparkle in the starlight. The cliffs shimmer with sharp crystalline edges, and entire valleys glint like polished glass. Not a gemstone in a jeweler's case, but a whole planet made mostly of crystallized carbon. These are the so-called diamond planets, carbon-rich worlds that push our imagination right to the edge of science fiction. Except they are not fiction at all. Here is the shock. Astronomers already believe diamond planets may actually exist. The first strong candidate was discovered orbiting a pulsar, a dead star spinning with incredible force. This planet, known as PSR Jason 191438b, is so dense that scientists think it may be the remains of a former star whose matter has crystallized into carbon. In plain language, that means it could be a planet-sized diamond locked in orbit around the corpse of a sun. Let that sink in. Somewhere out there, a literal jewel larger than Earth is drifting through space. And here's what makes it even more fascinating. These worlds are not rare fantasies. The building blocks of diamond planets exist all over the galaxy. If a planet forms around a star with more carbon than oxygen, chemistry takes a different route. Instead of creating silicate rocks like Earth, the planet's crust and mantle could form with huge amounts of carbon, compressed under insane pressure into diamond. That means whenever the ratios are right, nature might naturally sculpt planets of glittering stone. But this is not just about beauty or wealth. Think of what it means for the idea of habitability. A diamond planet would be brutally alien. The crust would be hard and unyielding, with no tectonic plates like Earth's. Volcanoes might erupt carbon-rich lava, spewing out tar, like substances instead of molten rock. Oceans as we know them might never form, because the surface would lack the balance of minerals needed to hold water. The atmosphere, if one even existed, could be toxic, heavy with methane or carbon monoxide. In other words, what looks dazzling on the outside may be completely inhospitable on the inside. And yet, here comes the validation. Even on Earth, diamonds are not symbols of life, but of pressure and transformation. They are born in darkness, miles below the surface, where heat and force shape something rare out of something common. If diamond planets exist, they remind us that the universe is not only generous with life, but also extravagant with possibility. It is not content to just make copies of Earth. It experiments, it diversifies, it creates worlds that seem like dreams. A diamond planet may not host oceans or forests, but its very existence proves how creative cosmic evolution really is. Now imagine what it would feel like to stand there. The sky might be dim, the air unbreathable, but the ground would sparkle with every step. The mountains would shine like glass cathedrals, and the horizon would gleam with sharp brilliance. It would be stunning and terrifying at the same time. A beauty too harsh to touch, a jewel too massive to ever hold. If humans ever reached such a place, the temptation would be overwhelming. Not because we could mine it. A diamond planet would be far too vast to strip, but because it would shatter our sense of value. A diamond on Earth is precious because it is rare. On a carbon world, it would be nothing but dirt. And here is a deeper point. We often tie value to scarcity, but the universe does not think in terms of our markets or our desires. To the cosmos, diamonds are just one possible outcome of chemistry and gravity. What we prize as priceless gems might be as common as dust elsewhere. That realization can either humble us or thrill us, depending on how we look at it. And finally, the tease. If diamond planets are real, then the universe is hiding treasures stranger than our wildest stories. Not just carbon worlds, but planets of iron, planets of ice, planets drenched in methane or cloaked in fire. Each one reminds us that Earth is only one version of what a planet can be. Somewhere out there, entire star systems may be glittering with jewels too vast to ever be claimed, waiting not for miners, but for dreamers who simply want to see them shine. Diamond planets are not just beautiful. They are proof that the universe does not care about limits. It builds worlds that dazzle, worlds that defy expectation, and worlds that remind us that the line between science and wonder is thinner than we think. Gas giants with habitable moons. Think about this for a moment. When we imagine other worlds, we almost always picture planets, rocky spheres like Earth, with continents, oceans, and skies. But what if the most promising places for life are not planets at all, but moons? Not small, gray rocks like our moon, but vast, Earth-sized moons orbiting gas giants. Imagine standing on a world where the night sky is dominated by a massive striped planet filling half the heavens, its storms swirling like living art, its rings stretching wider than you can comprehend. Every sunrise would be a reminder that your world is not alone. You are part of a miniature solar system. Here's the shocker. Gas giants like Jupiter and Saturn already have dozens of moons, and a handful of them show conditions that could support life. Europa has a hidden ocean beneath its icy crust, warmed by tidal forces from Jupiter's pull. Enceladus, orbiting Saturn, sprays plumes of salty water into space, proof of liquid seas under its frozen surface. Titan, also around Saturn, has rivers and lakes, not of water, but of liquid methane and ethane. These are just moons in our own backyard. Now scale that up to exoplanetary systems. If gas giants are common, and they are, then habitable moons around them might be everywhere. The real frontier of life in the universe may not be planets, but the moons that dance around them. And here's what makes them extraordinary. A large moon orbiting a gas giant gets more than just energy from its star. It also gets heat from tidal flexing, the constant stretching and squeezing caused by the planet's gravity. That means a moon could stay warm and habitable even if it is far from the star's traditional habitable zone. In other words, habitable moons break the rules. They open up the possibility of life thriving in places we used to think were impossible. Far from sunlight, deep in the outer reaches of star systems. Now picture what life on such a moon would mean for its inhabitants. Nights would never be truly dark. The gas giant would loom above like a permanent guardian, its cloud bands glowing, its rings casting shadows across the land. Other moons might appear as bright stars streaking through the sky, entire neighboring worlds visible with the naked eye. Instead of one sun and one moon, the people there would live under a sky full of shifting giants, a cosmic reminder every night that they are part of something larger than themselves. Here's the validation. On Earth, humans have always been shaped by the skies. Ancient civilizations aligned their temples to the stars, their calendars to the moon, their myths to the movements of planets. Imagine how much deeper that sense of connection would be on a habitable moon. Their calendars might not just track the seasons, but the dance of multiple moons. Their art might reflect the storms of their parent planet. Their religions might speak of being children not of the star, but of the giant that dominates their heavens. Life on such a moon would be defined by cycles, by tides, by the constant presence of a world so large it feels divine. But it is not just imagination. Scientists are already hunting for exomoons, moons orbiting exoplanets, with the hope of finding the first truly Earth-like environment outside our solar system. A big enough moon around a gas giant could have an atmosphere, liquid water, even continents and oceans. It would have day and night like Earth, but also eclipses when the gas giant blocks the star, plunging the world into sudden twilight. Entire ecosystems might evolve to handle these cycles of light and shadow. And now the tease. If habitable moons are real, they may be the most common cradles for life in the galaxy. Not rare jewels, but countless homes circling the great giants of space. Civilizations out there might not think of themselves as living on planets at all, but as children of moons. Their stories, their cultures, their very idea of the cosmos would grow from the sight of a giant in the sky that never leaves them. Gas giants with habitable moons are not just science fiction. They are mini solar systems of possibility, each one a reminder that life may not only adapt to the rules of the cosmos, it may thrive in the shadows of giants. And if we ever find them, we may realize that we were never really looking in the right place. The true promise of life in the universe might be orbiting not around suns, but around the silent, majestic giants that rule the night, planets orbiting multiple suns. Imagine waking up to a sunrise, but not just one. The horizon glows first with a pale amber light, then a second sun rises, bathing the land in a deeper gold, and sometimes even a third star climbs into the sky. Shadows stretch and bend in strange directions, colors shift and overlap, and the sky becomes a living painting of fire. This is not science fiction. These are the skies of planets orbiting multiple suns. Now for the shock. Binary star systems are not rare. In fact, most stars in our galaxy are locked in pairs or trios. That means our single, Sun-Earth, is actually unusual. And if planets can orbit these systems, which we now know they can, then double and triple sunrises are not just possible, they may be common. The first confirmed example was a planet called Kepler-16b, discovered in 2011, orbiting two suns. To anyone standing there, the world would look like a scene pulled straight from the movies, except it is real. We are not imagining this anymore. But here's where it gets even stranger. Multiple suns do not just create spectacular skies, they shape entire climates and seasons in ways we can barely wrap our heads around. Imagine two stars tugging on a planet with their combined gravity. Its orbit might be stable, but the light and heat would constantly shift as the stars dance around each other. That could mean wild seasonal swings, scorching when both suns are up, freezing when they set, or it could mean long stretches of balanced warmth if the stars align in just the right way. Each sunrise and sunset would not just mark the passing of time, it would shape survival. And yet, here comes the validation. Planets in multi-star systems might actually have advantages. Think of energy. Two suns mean twice the light for photosynthesis, twice the power for sustaining ecosystems. Alien plants might evolve to absorb one wavelength from the first sun and another from the second, creating landscapes with colors we have never seen. On a planet with three suns, the sky could shift between surreal hues as the stars cross paths. Life would not just adapt, it would flourish in ways we cannot predict. Now picture the human experience of living under multiple suns. Our entire sense of time and rhythm would be rewritten. Days might be endless if one sun always followed the other. Night might be rare, a fleeting luxury, when all the suns dip below the horizon together. Imagine cultures built around that cycle. Festivals during the rare nights when darkness falls. Myths of twin or triple gods walking across the sky. A spiritual bond with the heavens far deeper than anything we have known, because their skies would never be still. Even psychologically, the effect would be profound. Humans on Earth already tie emotions to light. We feel joy when the sun shines and melancholy during long gray winters. On a double sun world, the very mood of the planet might swing with the rhythms of the heavens. Two dawns would mean twice the hope, twice the renewal each morning. Two sunsets would mean twice the beauty, twice the reflection each evening. Life would not just be about surviving, it would be about living in a perpetual dialogue with the sky. And here is the tease. If most stars in the galaxy come in pairs, then planets with multiple suns might be the rule rather than the exception. That means the iconic single sunrise we experience on Earth may actually be the rarest kind of dawn. For countless alien civilizations out there, a sky with 2 or 3 suns would not be exotic. It would be normal. We might be the odd ones, the lonely children of a solitary star. Planets orbiting multiple suns remind us that our sense of what is ordinary is just perspective. We call Earth typical only because it is all we know. But in reality, the universe is painting skies we cannot imagine with double and triple dawns blazing across alien horizons. And if we ever stand on one of those worlds, watching 2 or 3 suns rise together, we may finally understand just how small our version of normal really is. Ringed planets, close your eyes and imagine this. You walk out at night, expecting a quiet sky filled with scattered stars. Instead, the heavens are dominated by a glowing band that stretches across the entire horizon. Not faint like the Milky Way, but blazing, icy shards and rocky fragments catching starlight, bending it into silvers and golds. It looks like a celestial crown wrapped around your planet. You do not just see stars above, you see architecture. A structure so enormous, so impossible, that it defines your world. This is life under rings. Here's the shock. Saturn's rings, the most famous in our solar system, already stretch more than 170,000 miles wide. If they were visible from Earth, they would fill our skies in ways we can barely imagine. And yet Saturn is not unique. Rings are not rare jewelry in the cosmos. In fact, astronomers have already spotted worlds with rings hundreds of times larger. In 2012, a planet called J127b revealed a system of rings so massive that, if you stood on a moon nearby, they would dominate every inch of the sky. Forget constellations. Forget stars. You would grow up under a ceiling of light so vast it would block out the universe itself. But rings are not just pretty ornaments. They are scars. They are made from shattered moons, torn apart by gravity, or from dust and ice that never managed to form into a planet. Every glowing fragment is a story of destruction, and yet, together, they form beauty. Imagine looking up and knowing that above you spins the wreckage of ancient worlds. Your sky would be a memorial to cosmic violence, but also a reminder that from chaos, something breathtaking can emerge. Now here's the validation. Rings shape more than the sky. They can change weather by casting shadows across a planet's surface. They can influence magnetic fields, alter atmospheric chemistry, even feed material back into the planet itself. On Earth, our climate is shaped by oceans and mountains. On a ringed planet, the sky itself is part of the ecosystem. Imagine farmers timing their planting not only to seasons, but to when the rings dim the sunlight. Imagine animals evolving to navigate a world where the sky never looks the same twice, glowing brighter or fainter as the rings tilt with the seasons. And think about daily life. On Earth, the moon inspires stories, poems, music. On a ringed planet, the rings would dominate art, culture, and myth. Children might grow up tracing their hands against the glowing arcs, making wishes on the patterns of light. Civilizations might build temples aligned with the exact angle where the rings catch fire at sunrise. Nights would never be truly dark. The rings would glow like lanterns, bathing the world in a permanent twilight shimmer. Darkness, true, absolute blackness, would be a rarity, maybe even something feared or revered, but beauty would come with danger. Massive rings are not stable forever. They shift, grind, and shed material. That means meteor showers could rain down more often, fragments plunging into the atmosphere with terrifying brilliance. For any civilization reaching into space, the rings would be both a gift and a curse, a crown of light above your world, and a wall of death for any ship trying to escape it. To travel beyond the atmosphere, explorers would have to navigate rivers of ice and stone, dodging millions of fragments. Every launch would feel like threading a needle through chaos. And now let's go deeper. Imagine the psychology of living under rings. On Earth, we look up at the stars to feel small, to remind ourselves that the universe is bigger than us. On a ringed planet, you would not need stars to feel that. The rings themselves would give you that sense every single day. No one under such a sky would doubt the scale of the cosmos. No one would need to imagine eternity. It would be staring them in the face. Every morning, every night. Life on that planet would always carry the weight of wonder. What would their myths be like? Perhaps they would see the rings as a barrier, separating the mortal world from the heavens. Perhaps they would tell stories of ancient gods whose shattered thrones still circle above. Or maybe they would see them as guardians, a protective crown around their home. On Earth, the sky is a canvas for imagination. On a ringed planet, the sky is already filled with stories written in light. And here's the tease. If rings can form so easily, from moons breaking apart from debris left behind, then they might not be rare. There may be countless planets across the galaxy crowned with luminous arcs. For us, Saturn is a jewel, a curiosity. But out there, ringed worlds could be normal, each one a reminder that the universe does not just build for function. It builds for spectacle. Ringed planets are not just cosmic decorations. They are living, evolving monuments to both destruction and beauty. They remind us that the universe is not silent and plain, but extravagant. And if one day we find ourselves under a sky with rings brighter than Saturn's, stretching wider than anything we have ever seen, our idea of what a planet can be, what home can be, will never be the same again. White dwarf systems, a star once as brilliant as our sun, burns through its life and collapses into something no larger than Earth. The fire is gone, the brilliance is gone, and all that is left is a dense, dim ember. A white dwarf. From a distance it looks like nothing more than a fading spark in the dark. You might think that when a star dies, its planets die too, but the universe rarely lets endings be that simple. Around these stellar remnants, survivors linger. Worlds that should have been destroyed keep orbiting, clinging to existence in a system that has already ended once before. Here is where the shock hits. A white dwarf is unbelievably dense. Imagine the mass of the sun packed into something the size of our planet. A teaspoon of its matter would weigh tons on Earth. It is the husk of a star, still glowing faintly, still radiating heat, but no longer alive. And yet, despite that violence, astronomers have found planets circling these corpses of stars. Some are charred remains that manage to endure the fiery death throes. Others may be new worlds, formed from the rubble of shattered siblings. A system reborn in the ashes of catastrophe. Think about what that means. To orbit a white dwarf is to live in the aftermath of cosmic annihilation. Before the star collapsed, it would have swelled into a red giant, swallowing inner planets, vaporizing atmospheres, scorching everything nearby, and still some worlds endure. We have already seen the evidence. Fragments of planets literally raining down onto white dwarfs, their materials leaving chemical scars on the surface of the dead star itself. It is proof that planetary systems are not erased in neat, clean endings. They survive in strange, haunting ways. And here is the validation. White dwarfs might not just host wreckage, they could also cradle life. In theory, a planet orbiting close enough to the faint glow of a white dwarf could have the right temperature for liquid water. Unlike massive, fiery stars that live short, chaotic lives, a white dwarf cools slowly, over billions of years. That means a habitable zone, a narrow band where warmth lingers, could remain stable for an unimaginably long time. Longer than the main life cycle of most stars. If life managed to arise there, it could have more time to evolve and adapt than it ever would around a sun like ours. Survival, after all, often finds strange paths, but picture what the sky would look like. From the surface of such a planet, the white dwarf would not blaze like our sun. It would glow like a ghostly lantern, faint but steady. Night and day would blur into something softer, dimmer, more dreamlike. Shadows would not be sharp but pale, as if the whole world lived under permanent twilight. A civilization born there might not even have a word for true sunlight. Their myths might speak of an ancient age when the star was young and fire filled the sky. Stories passed down about a brightness they never experienced themselves. To them, the pale star above would not feel like loss. It would feel like home. And yet, there is danger. The white dwarf systems are not gentle. The planets that survive orbit close, often so close that the star's gravity stretches them, tearing at their crusts. Radiation can still leak out in bursts, sterilizing surfaces, and any civilization daring to explore space would be confronted constantly by reminders of death, planetary debris fields, asteroid belts born from shattered worlds, scars in the light of their pale sun. Imagine launching into orbit and seeing broken fragments of what could have once been a sister planet circling forever in silence. To live in such a system is to live with memory all around you. Still, survival itself is powerful. Psychologically, there is something almost poetic about worlds orbiting the remains of a dead star. It speaks to resilience, to endurance. On Earth, we see endings as final. The sun sets, a flame burns out, a star dies. But in the cosmos, endings often give way to strange new beginnings. White dwarf systems are proof that survival does not mean unchanged. It means adapting, clinging, finding a new balance in the ruins. If life exists there, it would be life born not in the light of creation, but in the dim glow of persistence. And here is the tease. If we can already detect these systems, if we can already see fragments of planets raining down on stellar remnants, then what else might we find as our instruments sharpen? Perhaps entire worlds that endured the storm, still intact, orbiting like loyal companions around their ghostly star. Perhaps even civilizations that arose long after the main event, unaware of the brilliant life their star once lived. To them, the universe would always seem dim, and only when they reached beyond their star would they learn that once, long ago, their home was born from fire. White dwarf systems are not quiet tombs. They are survivors' tales written in the language of gravity and light. They remind us that even in the face of collapse, even in the aftermath of total destruction, something can remain, something can adapt, something can continue. And maybe, in those strange twilight worlds, survival itself becomes the greatest story the universe has to tell. Black hole worlds, a sky with no sun, no star rising or setting, just darkness stretching endlessly, broken only by the glow of a warped horizon. In the center of it all is a shadow so heavy, so absolute, that nothing, not even light, can escape. This is life in the grip of a black hole. And yet, against every instinct that screams impossible, some scientists wonder, could worlds exist here? Could there be habitats orbiting the most destructive objects in the universe? Here comes the shock. Black holes are not just cosmic monsters. They are also engines of unimaginable energy. Matter falling toward them spirals into an accretion disk, heating until it glows hotter than stars. That glow, that radiation, could provide light and heat for nearby worlds. The black hole itself, paradoxically, could become the heart of a system. Imagine a planet locked in orbit, skimming the edge of destruction, but kept alive by the energy pouring from the chaos. It sounds like science fiction, yet mathematically it checks out. The physics allows it, but to live near an event horizon is to live at the edge of sanity. Time itself bends there. The closer you orbit, the slower time passes compared to the outside universe. What feels like an hour on your planet could be years, centuries, or millennia elsewhere. Think about what that would mean for life. A civilization could rise and fall in the blink of an eye to the outside galaxy. To them, time feels normal. To the universe, they are moving in slow motion. Black hole worlds would not just be strange physically. They would be strange historically. They would be worlds out of sync with everything else. Now let's validate the idea. Planets could exist in safe orbits far enough from the black hole to avoid being swallowed, but close enough to harvest energy. Some scientists even propose that advanced civilizations could build structures, Dyson sphere-like megastructures, around black holes to harness rotational energy, because a spinning black hole actually stores staggering amounts of usable power. Unlike stars, which eventually burn out, a black hole can last for trillions upon trillions of years. That makes it one of the most reliable long-term energy sources in the cosmos. So if life ever wanted stability, the irony is that the safest home might be orbiting the most feared object we know. And picture the sky from one of these worlds. Above you, stars would not look normal. Their light would curve and smear as space, time bent it around the black hole. The horizon would shimmer like liquid glass, bending reality itself. At the very center, no sun, no glow, just an eternal void where physics collapses. Your entire culture would grow up under a sky that teaches you one thing: the universe is not straight. It is curved, twisted, alive with hidden rules. Imagine how that would shape philosophy. Imagine art inspired by horizons that do not behave, light that moves like waves in water, time itself experienced differently from one orbit to another. But danger is everywhere. Radiation from the accretion disk could sterilize a planet unless it had powerful shields or a thick atmosphere. Tidal forces could stretch entire worlds, pulling oceans and continents like taffy. To survive here would mean adapting to constant extremes. Maybe underground habitats, maybe evolving bodies resistant to bursts of energy. Or maybe intelligence would emerge not in biology at all, but in machines built to thrive in the shadow of chaos. The universe does not care what form life takes, only that it finds a way. Think about the psychology of such beings. On Earth, we look at the sun as a giver of life, steady and warm. On a black hole world, the heart of your system would be an absence, a devourer. Your myths would not describe a nurturing parent in the sky. They would describe a hungry void that must be respected, feared, maybe even worshipped. Entire religions could form around the idea that time and life itself come from circling the edge of nothingness. The event horizon would be your god, silent, invisible, but inescapable. And here is where it gets even stranger. A black hole can act like a lens, magnifying distant galaxies as light bends around it. From the surface of your world, the night sky might reveal views of galaxies billions of light years away, magnified into glowing arcs. Inhabitants of such a planet could see farther into the universe than we ever could with telescopes. Their very sky would be a cosmic observatory, showing them the grand structure of everything. They would grow up already knowing that the universe is enormous, because it would stare at them every night. Now, the tease. If black hole worlds are possible, if they can orbit safely, harvest energy, maybe even sustain life, then we have to wonder how many are out there. Black holes are everywhere, scattered across galaxies, relics of dead stars. Some sit quietly, others blaze with accretion disks bright enough to outshine entire galaxies. And around them, who knows what worlds might cling to orbit. To us, they are places of terror. To someone else, they might be the perfect cradle. Black hole worlds remind us of something profound. The universe does not follow our instincts about life or death, creation or destruction. What we fear as an end could just as easily be a beginning. The most terrifying object in the cosmos could also be the longest, lasting source of life and energy. And if one day we find a civilization orbiting the darkness, living in the glow of an impossible horizon, we will know that even in the places we thought uninhabitable, survival has already written its story. Mega-continent planets. You stand on a shore, looking out not at an ocean that stretches endlessly, but at land. You travel for weeks, months, even years, and never once see the sea. The horizon always ends with more mountains, more valleys, more forests, more deserts. This is a mega-continent planet. A world not broken into scattered islands and continents like Earth, but dominated by one colossal landmass that swallows the globe. Now here's where it gets shocking. Earth itself has had supercontinents in the past. Pangaea was the most famous, existing about 300 million years ago. Before that, others formed and broke apart in cycles lasting hundreds of millions of years. But Earth always reset, splitting its continents again. Now imagine a planet where that never happens. A planet where tectonic plates are sluggish, or the crust is so stable that once a supercontinent forms, it never breaks apart. You are left with a world of endless land. Oceans exist, but they are shoved to the edges, almost like an afterthought. That changes everything about climate, life, even civilization itself. Because here's the catch. Oceans are not just pretty backdrops for beaches. They are engines that move heat around the globe. They keep climates balanced, circulate nutrients, and create natural barriers that separate species and cultures. On a mega-continent planet, that system collapses. The interior of the landmass could be brutally dry, cut off from the moderating influence of the sea. Deserts larger than anything on Earth could stretch for thousands of miles, places where rain almost never falls. At the edges, near the oceans, storms might rage constantly, dumping endless water, while the middle remains bone dry. That means ecosystems would be divided in extreme ways, lush coastal strips teeming with life, and vast barren interiors where survival is nearly impossible. But think about evolution here. On Earth, separation by oceans allowed species to diversify. That is why Australia developed creatures unlike anywhere else. A mega-continent planet would erase that. Species would spread widely across the same land, competing directly for the same resources. Evolution might favor generalists, tough, adaptable creatures that can handle a variety of environments, over specialists. Or, conversely, isolated pockets created by mountains and deserts could lock species away for millennia, creating tiny oases of diversity surrounded by hostile wastelands. Life would still find a way, but it would look very different from what we know. And then there's the human question. What would civilizations look like on such a planet? Without oceans to divide them, cultures would spread across the land far more easily. That sounds like it would unify people, but history suggests something else. On Earth, large unified territories often collapse under their own weight. Vast empires fracture, languages splinter, identities harden. On a mega-continent planet, you could have colossal states spanning millions of square miles, but the friction of ruling such spaces might lead to constant cycles of rise and fall. Entire regions could vanish from memory because there are no seas to preserve contact or trade. Ironically, even with all the land connected, people might feel more isolated than we do now. And yet, imagine the possibilities for exploration. On Earth, when you cross an ocean, you know you are reaching a different world. On a mega-continent planet, crossing into a new region could be like stepping onto another planet entirely. You might leave behind icy tundra and, after months of travel, emerge into deserts hotter than anything in the Sahara. Keep going, and you could climb mountains taller than Everest, then descend into jungles that stretch unbroken for thousands of miles. The diversity would not be in separation by seas, but in the sheer scale of the land itself. To explore such a planet would feel endless, even if technically you were never leaving the same continent. Now let's validate this further. From a planetary science perspective, megacontinents are entirely plausible. Tectonics depends on the thickness of the crust, the heat of the mantle, and the flow of convection currents below. Some planets may have crusts so stable that continents simply do not break. Others may have weaker plate activity, meaning collisions happen less often, leaving land to merge and stay fused for eons. There is no law that says Earth's balance is the only way. In fact, when astronomers model exoplanets, they often assume many could be locked in permanent continental configurations. But here is the most fascinating part. Climate models suggest that megacontinents can push planets into extremes. If the landmass is too large and deserts dominate, a planet might lose its ability to recycle carbon dioxide effectively, destabilizing temperatures. That could mean swings between ice ages and greenhouse states far more violent than Earth's. In other words, a megacontinent planet might be less stable, forcing life to adapt constantly or face extinction. It is a harsher world, but not an unlivable one. If anything, that harshness could drive resilience in its species. And picture the night sky culture. On Earth, oceans guided navigation. Stars were maps across seas. On a megacontinent planet, people would orient themselves across endless land. Perhaps giant mountain ranges or desert formations would become the cultural equivalents of oceans. Barriers defining identity, myth, and travel. The idea of being a wanderer would be tied not to sailing across waves, but to trudging for months across deserts where no rain falls. Exploration would still shape the human spirit, but through different frontiers. Now, here's the tease. If megacontinent planets are common, and if they can stabilize long enough to host life, then entire civilizations could rise there. Civilizations who never knew what it meant to live beside an ocean. To them, the very concept of a world divided by seas might sound alien, almost absurd. And yet, they could look up at the stars and wonder, just like us, if there are other kinds of worlds out there. Worlds broken into scattered islands. Worlds where survival is defined not by endless land, but by endless water. Megacontinent planets are a reminder that even familiar ingredients, land, water, air, can create alien realities when arranged differently. They show us that habitability is not just about distance from a star or presence of oxygen. It is about the balance of everything, the geography, the cycles, the structures that shape life's possibilities. One vast continent is enough to change everything. Super ocean planets. Close your eyes and picture this. You are standing at the edge of the sea, except there is no land behind you, no continent to return to, no mountains or deserts or forests, just water. You dive in, and the ocean does not stop. It goes down not for a few miles like on Earth, but for hundreds, even thousands of miles. You could swim forever and never reach the bottom. You could sail forever and never find land. This is a super ocean planet, a world where water has won, where the surface is a single endless ocean stretching across the entire globe. Now here is where it gets shocking. Earth feels like a water world, but it really is not. 70% of our surface is ocean, yes, but compared to the entire planet, it is just a thin skin. If you shrank Earth down to the size of a billiard ball, the oceans would be no deeper than a coat of paint. On a superocean planet, that coat becomes a blanket miles thick, so deep that light never touches most of it. Pressure crushes everything below, creating conditions so alien that life would have to rewrite the rules to survive. And yet, life could thrive here. Scientists believe water is one of the most important ingredients for habitability. It is a solvent, a medium where molecules bump into each other, where chemistry can become biology. A superocean planet would have more of that than anywhere else. Imagine billions of square miles of surface for photosynthesis, entire layers of ecosystems floating in different depths, gigantic creatures roaming through endless currents with no shores to block their migration. In a sense, such a world could be more alive than Earth ever was. But let's validate the science. Astronomers already suspect that superocean planets exist. When we study exoplanets larger than Earth but smaller than Neptune, many of them seem to have densities that do not match a purely rocky world. They are too light for their size, meaning they may hold massive envelopes of water. These are sometimes called water worlds or aquaplanets. The pressure inside could create exotic ices, Ice 7, Ice 10, not like the ice cubes in your freezer, but crystalline solids formed under crushing weight. These exotic ices might form deep mantles beneath the ocean, separating the liquid water from the rocky core. That changes how the geology and chemistry of the planet work. Think about that for a second. On Earth, life relies on the carbon cycle, volcanism, and plate tectonics to recycle nutrients. On a superocean planet, with oceans so deep that the crust is sealed off by layers of high-pressure ice, that connection might be cut off. The ocean could be nutrient-poor unless other mechanisms evolve. Maybe hydrothermal vents that still reach the surface layers, or storms so violent that they stir the chemistry of the water. It could be a harsher place, but that does not make it empty. It just means life there would be forced to adapt to challenges we can barely imagine. And here is where it gets really fascinating. Imagine civilizations on such a planet. Without land, there are no mountains to mine, no forests to harvest, no deserts to cross. There are only waves, storms, and endless horizons. Technology would have to evolve differently. Maybe floating cities drifting like archipelagos. Maybe species that never develop fire, but instead master chemistry, biology, or even geothermal heat from the planet below. Their myths would not be about conquering mountains or taming deserts. They would be about the endless ocean, about the monsters of the deep, about the storms that rise without warning and swallow entire fleets. Now imagine their psychology. On Earth, we dream about traveling across oceans to discover new lands. On a superocean planet, that dream would not exist. Every voyage ends the same way: more water. Their explorers might turn their eyes upward far earlier than we did, because the sky would be the only frontier beyond the sea. For them, space itself might feel like the land they never had, the only place where boundaries could exist. That changes everything about how a civilization thinks, how it dreams, how it builds its future. Picture the storms here. With no continents to break the winds, hurricanes could grow larger than anything we know, circling the planet endlessly. Waves taller than skyscrapers could crash across the surface, reshaping ecosystems with every cycle. For us, those storms would be disasters. For life there, they would be routine. Creatures might grow armored, built to withstand constant pressure and chaos. Floating cities might be designed to sink temporarily, riding out storms underwater, only to rise again when the skies clear. Survival here means bending to the rhythm of the ocean, not resisting it. And now the tease. If super-ocean planets are real, and the data suggests they are common, then the galaxy may be filled with worlds far wetter than our own. But wet does not automatically mean welcoming. Some may be sterile, sealed off from nutrients. Others may host entire biospheres hidden beneath their waves. And if intelligence evolves there, we may one day meet beings who have never set foot on solid ground, who cannot even imagine what a mountain or desert is. To them, our Earth might look alien, a place where the sea is broken apart, trapped between patches of rock. Super-ocean planets remind us that even something as simple as water can become strange when it dominates completely. They are at once familiar and alien, comforting and terrifying, and they may be the most common kind of habitable world out there. Endless oceans, endless possibilities, endless questions. Planets with toxic atmospheres. Imagine stepping onto a planet where the very first breath you take is the last. The air looks clear, the sky might even be blue or golden, but inside that beauty is poison. It could be ammonia thick in the clouds, chlorine misting across the horizon, or sulfuric acid burning through the raindrops. These are toxic atmosphere planets, worlds where the air is not just unbreathable, but actively hostile, a chemical gauntlet that life would have to wrestle with every second just to survive. And here's the part that shocks most people. Toxic atmospheres are not rare in the universe. In fact, Earth might be the oddball. Venus, our neighbor, is smothered in carbon dioxide so dense it creates a crushing greenhouse effect, with clouds of sulfuric acid that would strip the paint off a spaceship. Titan, Saturn's moon, has thick layers of nitrogen and methane, so cold that water is locked away like rock while liquid methane forms lakes and rivers. These are local examples, but when astronomers look beyond our solar system, they keep finding exoplanets wrapped in atmospheres that are chemical cocktails, places where oxygen as we know it is absent. Now, why does this matter? Because it reframes what we think is possible. We often imagine habitability as Earth, like air, nitrogen, oxygen, maybe some carbon dioxide. But toxic does not always mean lifeless. On Earth, extremophiles thrive in sulfur vents, in acid lakes, even in methane seeps at the bottom of the ocean. Life has proven again and again that what looks like poison to us is just chemistry to something else. So on a toxic atmosphere planet, life could evolve with biology tuned to breathe chlorine, or to metabolize methane, or to use sulfur the way we use oxygen. From their perspective, our air would be the poison. But let's pull this closer to human experience. Imagine what it would be like to live there. Every step outside would require shielding, not just from radiation or pressure, but from the very air. A tear in your suit is not a slow problem. It is instant agony. Your lungs seize, your skin burns, your eyes are destroyed. Colonies would have to be completely sealed, giant domes where the local atmosphere is kept out at all costs. The danger would shape culture. Safety drills would not be about fire escapes or earthquakes, but about what to do when the air itself tries to kill you. Children would grow up knowing they can never feel wind on their faces. The idea of breathing outside would sound like a fantasy, maybe even a myth. The science makes this even more fascinating. Planetary atmospheres are shaped by the chemistry of their surfaces and the radiation from their stars. A hot young star can strip hydrogen from a planet, leaving heavier gases like carbon dioxide or methane behind. Volcanic worlds can outgas sulfur compounds until the entire sky is yellow. Planets closer to their stars can build atmospheres so thick that pressure rises to crushing levels, like Venus. Others orbiting farther away can freeze gases into strange layers, creating hazes and smogs unlike anything we see here. Toxic is not exotic. Toxic is normal. Earth's clean, breathable air may actually be the exception, not the rule. But think about how that would affect discovery. When we eventually scan an exoplanet and detect chlorine in the air or high levels of sulfur dioxide, our instinct might be to cross it off as uninhabitable. Yet, we could be staring at a world rich with alien life that just does not play by our rules. To them, their skies are perfect. Their evolution built bodies that thrive in environments that would shred ours to pieces. And if they ever looked at Earth, they might call our air corrosive, deadly, insane. Oxygen, after all, is a highly reactive gas. On early Earth, when oxygen began to rise in the atmosphere, it caused one of the biggest mass extinctions in history. To the life that came before, oxygen was toxic. To us, it became the breath of survival. So now imagine intelligent civilizations on these chemical worlds. Their mythologies might treat the atmosphere not as something gentle, but as something fierce and divine, a force that takes life if disrespected. Their technology might evolve around filtering and shaping the air, turning poison into breath. Their art might be obsessed with skies, storms, clouds, the endless moods of an atmosphere that constantly tests them. And if they ever met us, they would find it hard to believe we walk casually under open skies, bare, skinned, breathing freely without thinking twice. To them, that would sound like magic. And here is the tease. Toxic atmosphere planets might not just be common. They might be the breeding grounds for some of the strangest forms of life in the galaxy. Worlds where acid rains are not catastrophes, but catalysts, where lightning and methane storms power alien metabolisms, where the skies we would call deadly are, for them, the skies of home. These planets remind us of something important. When we search for life, we cannot only look for Earth 2.0, we have to stretch our imagination, because in the end, life is not about comfort. It is about possibility, and possibility exists even under alien skies that would kill us in seconds. Carbon-rich worlds. Picture a planet where the very building blocks of reality are different from what we know. On Earth, everything begins with oxygen. Our rocks, our oceans, even our air. They all lean on oxygen as the dominant element. But now imagine a world where carbon takes the throne instead. A carbon-rich planet, sculpted not by the chemistry of Earth, but by a completely different set of rules. The landscapes, the skies, the minerals, the very possibility of life would all look alien, not because the laws of physics changed, but because the balance of chemistry did. And here is the part that stops you in your tracks. Worlds like this are not just science fiction. They are possible, even likely. Astronomers already suspect that stars with higher carbon to oxygen ratios may give birth to planets where carbon dominates. Instead of granite mountains like ours, you could see ranges of pure graphite or vast expanses of diamond formed under immense planetary pressure. Entire continents glittering with carbon crystals, not as jewelry, but as bedrock. A single planet in such a system could hold more diamonds than every mine on Earth combined. But to the locals, it would just be dirt. Now let's ground this in science. The chemistry of a planet is tied to its star. Our Sun has just enough carbon and oxygen to give Earth its oxygen-rich composition. But if a star forms from material richer in carbon, the dust and gas that coalesce into planets shift the recipe. Instead of silicate rocks, you get carbides. Instead of oceans of water, you might find oceans of hydrocarbons, thick tar like seas where methane and ethane replace what we call life's cradle. These are not far-fetched hypotheticals. When we measure exoplanets, many show signs that their densities and chemical signatures do not line up with Earth's blueprint. Some of them may very well be carbon-rich worlds hiding in plain sight. So what would that actually feel like? Imagine walking across a diamond plain, the surface glittering beneath a sun that burns slightly redder than ours. Mountains made of carbon compounds rise in sharp peaks, black and shining like obsidian. Rivers of liquid hydrocarbons flow where our rivers of water would. The air might not be breathable, at least not to us, but it could carry compounds that life there has evolved to use. To the beings who call it home, this is not strange. It is normal. They would see our blue oceans and granite cliffs as alien, maybe even unthinkable. The shocking part is how this chemistry could give rise to life. We are built on carbon already. It is the backbone of every protein, every strand of DNA, every cell membrane. Carbon's versatility is unmatched, which is why scientists think it is the most likely element to build life anywhere in the universe. But on a carbon-rich planet, the story changes. Instead of oxygen-powered metabolisms like ours, alien organisms might breathe methane or feed on hydrocarbons. Their cells might resist acid, but dissolve in water. Their evolution could be shaped by resources we cannot even touch without protective suits, and yet they would be as alive and as complex as we are, just tuned to an entirely different chemistry set. Now imagine civilization there. A world where diamonds are as common as dirt changes how value works. What we see as rare and precious, they might see as useless stone. Their economies would not revolve around gems or carbon-based fuels, because those would be everywhere. Instead, maybe oxygen, the very thing we take for granted, is the rare treasure. Maybe water, instead of being abundant, is a coveted substance mined from asteroids or traded between planets. Their myths would not tell stories of fire forged in wood or coal. They would tell stories of the rare drop of liquid water that gave life or the divine spark of oxygen that made breath possible. But let's not sugarcoat it. Carbon-rich planets may be harsh for us. The skies could be thick with smog like atmospheres, heavy with methane and soot. Rain could fall not as water, but as hydrocarbon droplets, leaving the surface sticky and dark. To us, that is inhospitable. But from another perspective, it is fertile ground. Just as Earth turned out to be perfect for us, a carbon planet could be perfect for them. And here is the tease. If carbon-rich worlds are out there, and the chemistry of the cosmos says they are, then they expand the definition of habitability far beyond what we imagined. Life does not have to look for Earth clones. It can bloom in tar seas, crawl across diamond continents, and breathe air we would call poison. For all we know, the galaxy could be filled with civilizations built on chemistry so different from ours that meeting them would feel like meeting reality itself turned inside out. Carbon-rich planets remind us of something deeper. The universe is not obliged to give us familiarity. It is obliged only to give us possibility. And possibility, in this case, looks like worlds that sparkle with diamonds, shine with black graphite mountains, and breathe air laced with alien chemistry. They are not Earth, and that is the point. They show us that nature's imagination is far greater than ours, and that life may already be thriving under rules we have not even learned to write. Planets with extreme winds. Try to imagine standing on a world where the air never stops moving. Not a gentle breeze, not even a hurricane by Earth's standards, but winds so violent they circle the planet endlessly at thousands of miles an hour. The ground itself might be solid, but the atmosphere above is a roaring ocean of storms, ripping across the skies with a power we can barely comprehend. These are planets of extreme winds, places where calm is a concept that simply does not exist. Here is what will stop you cold. Earth's strongest recorded wind gusts are around 250 miles an hour, the kind that flatten houses and send cars tumbling like toys. Now compare that with Neptune, where supersonic winds scream across the atmosphere at more than 1,300 miles an hour. That is faster than the speed of sound. Imagine an entire planet wrapped in storms so strong they would shred steel, and Neptune is not an outlier. Many gas giants and hot exoplanets we have discovered show signs of atmosphere circulation on a scale that makes our hurricanes look like ripples in a pond. Why does this happen? It comes down to energy. Winds are just air responding to differences in temperature and pressure. On Earth, the sun drives most of our weather. On gas giants, you have planets thousands of times bigger, sometimes with internal heat left over from their formation, blasting extra energy into their skies. On hot Jupiters, exoplanets that orbit dangerously close to their stars, the contrast is even more dramatic. One side of the planet can be heated to thousands of degrees, while the other remains in near darkness. That imbalance whips the air into constant, planet-wide storms. It is not just windy there. The entire world is a storm engine. But let's pull this into something human. Picture trying to live in a place like that. Every structure, every wall, every vehicle would have to be designed not for earthquakes or floods, but for the endless assault of the wind. You would never hear silence outside. The sound would be a constant howl, the background noise of existence. Going outdoors without protection would be suicide, not because you would suffocate, not because of radiation, but because the air itself moves faster than you can react. On a world of extreme winds, survival is not about building high towers. It is about burrowing down, clinging to the ground, finding ways to live where the atmosphere cannot tear you away. And the psychology of it is fascinating. Humans crave calm. We relax in stillness. We find peace in quiet mornings where the trees do not move. On a planet of endless storms, there is no such relief. Imagine growing up where children have never seen still air, never watched smoke rise straight upward, never known what silence outdoors feels like. Their myths might describe wind as a god, an ever-present spirit that cannot be escaped. Their art might obsess over spirals, waves, the endless motion of air. Their entire culture could be built on the idea that chaos is not temporary. Chaos is the natural state of the universe. But here is the twist. These planets may also be some of the most beautiful places imaginable. Think of Jupiter's Great Red Spot, a storm larger than Earth itself that has raged for centuries. Now imagine skies filled with bands of color, storms stacked on storms, lightning storms stretching across thousands of miles. Extreme winds do not just destroy. They also create patterns, movements, and displays we cannot see anywhere else. A world like this would be terrifying and breathtaking in equal measure. And let's not underestimate what this means for the search for life. We often assume that planets with extreme weather are uninhabitable. But here's the shock: even on Earth, life thrives in hurricanes, in the upper atmosphere, in jet streams. There are microbes that ride high-altitude winds for thousands of miles. Birds migrate using wind currents as highways. What if on another planet, entire ecosystems evolved to live in the air itself? Creatures with bodies built like sails, drifting endlessly, feeding on particles in the wind. They would never need ground. Their whole lives could take place in a sky that never stops moving. To us, that seems impossible. But if the winds are permanent, life will adapt. Now imagine the first explorers landing on such a planet. Their ships would be battered before they even touched the ground. Their instruments would constantly need recalibrating. Every step outside would be a battle, not against gravity or temperature, but against an invisible force hammering them from every angle. And yet, if they looked up, they might see skies alive with motion. Colossal storms glowing with lightning, bands of color twisting like brushstrokes across the heavens, clouds stretched into endless rivers flowing at supersonic speeds. It would be as terrifying as it is unforgettable. And here is where the tease comes in. Extreme wind planets remind us that weather is not just background. On some worlds, weather is the world. It shapes landscapes, it defines survival, it becomes the constant heartbeat of existence. These are places where calm never comes, where silence never falls, where the atmosphere itself is the ruler of all. And in those roaring skies, life may already be writing stories we cannot yet imagine. Exoplanets with unknown atmospheric signatures. Sometimes the most unsettling discoveries are not the ones we expect, but the ones that make no sense at all. Astronomers point their telescopes at distant worlds, break down the light filtering through their atmospheres, and what they find is not the familiar fingerprint of oxygen or carbon dioxide or methane. Instead, they find signals that do not match anything we know, chemical recipes that do not line up with our models, skies that should not even exist. These are exoplanets with unknown atmospheric signatures, worlds that leave us staring at data, scratching our heads, and quietly wondering if nature is stranger than we ever imagined. Here is where it gets shocking. When light passes through a planet's atmosphere, certain wavelengths get absorbed depending on the gases present. It is like reading a barcode of chemistry. On Earth, this barcode would show water vapor, oxygen, nitrogen. But in recent years, as our instruments have sharpened, we have picked up exoplanet signals that do not fit the pattern. Some planets show missing lines where gases should be. Others show extra lines that hint at chemicals that should not exist under the conditions we think are there. In plain language, the sky is lying to us. Why is this happening? There are a few possibilities, none of them simple. It could be exotic chemistry at work, molecules we have never seen in planetary atmospheres before. It could be haze particles, strange aerosols made of metals or silicates that scatter light in unexpected ways. Or, and this is the part that keeps scientists awake at night, it could be something we are not even looking for, something outside our models entirely. Unknown signatures mean one thing. Our understanding of atmospheres, which feels solid on Earth, is not universal. Now let's make this human. Imagine standing under a sky you cannot explain. You look up and the air around you glows with a faint hue you do not recognize. Your sensors tell you there are gases swirling above your head, but they refuse to line up with anything in your databases. You breathe in, and you realize you have no idea what you are breathing. That is the unsettling truth of these exoplanets. They remind us of how fragile our certainty is. We assume the universe runs on rules we have mastered. Then the data arrives, and it whispers back, "Not so fast." And here is something wild. Some of these unexplained signals appear on planets that are otherwise Earth, like in size or temperature. That does not mean they are habitable, but it means their chemistry might be doing something unique, something outside the script we keep rehearsing. For years, we have told ourselves to look for biosignatures like oxygen, ozone, or methane as possible hints of life. But what if life elsewhere rewrites the script? What if biology there produces gases we would dismiss as noise? If we only look for what we know, we might walk right past evidence of life waving its hand at us in the form of an unknown signal. Here is where psychology kicks in. Humans hate ambiguity. We like answers. We like to check boxes. When the data comes back and it does not fit, our instinct is to smooth it over, to assume the instruments are wrong, to shove the mystery aside until it behaves. But science thrives on the uncomfortable. Unknown atmospheric signatures are not failures. They are invitations. Every unexplained spectrum is a door cracked open into chemistry, physics, maybe even biology we have not yet met. And that is terrifying, because it means we are not as far along in understanding the universe as we like to think. Now imagine an alien civilization looking back at us. If they were scanning Earth, they would see oxygen, methane, water vapor, ozone, a combination that screams life to anyone who knows how unstable those gases are together. But what if their models do not include oxygen chemistry? What if to them, our atmosphere looks like nonsense, an unexplainable fingerprint that does not match anything in their books? To them, we might be the planet with the strange atmospheric signature, the one that refuses to fit the rules. Suddenly, the question flips. We are not just hunting for the unknown. We might be the unknown. And here is the tease. As telescopes like the James Webb Space Telescope and future observatories keep scanning the skies, the number of these strange signatures will only grow. Some will turn out to be dust or haze or mistakes in the data, but some will not. Some will reveal entire categories of planetary chemistry we have never thought of. Some might hint at processes we cannot explain without daring to whisper the word life. Unknown signatures are not dead ends. They are the universe telling us we still have more questions to ask, and in those questions, there might be the first glimpse of something truly alien. These worlds do not comfort us. They do not hand us easy answers. Instead, they point at our own arrogance and say, "You thought you had this figured out. You thought Earth was the template. But the cosmos is deeper, stranger, and far more creative than your models allow. And somewhere out there, under alien skies glowing with colors we cannot name, the rules of chemistry are being rewritten right now. Planets on the edge of the habitable zone. Think about balance for a second. Life, as far as we know it, exists only because Earth sits in a razor-thin band of space around the sun where conditions are just right. Too close and oceans would have boiled away. Too far, and they would have frozen solid. This region has a name: the habitable zone. But what happens when a planet lies right at the edge of that line, dangling between possibility and impossibility? These are the planets on the edge of the habitable zone, worlds that tempt us with the idea of life, but threaten to snatch it away with the smallest change. Here is where it gets unsettling. On Earth, a shift of only a few degrees in global temperature has been enough to trigger ice ages and mass extinctions. Now imagine a planet that spends its entire lifetime in a constant tug of war, hovering just barely warm enough or just barely cold enough to hold on to liquid water, a tiny wobble in orbit, a slightly brighter star, a stronger greenhouse effect, and suddenly that world tips from being a candidate for life to being a dead rock or a frozen wasteland. These are not stable havens. They are cliff edges. And life, if it exists there, is balancing on a knife's edge every single day. Why does this matter so much? Because most of the exoplanets we have discovered so far that seem Earth-like are not perfect copies of Earth. They often sit at the margins. Some circle stars that burn hotter, pushing the habitable zone outward. Some orbit cooler, dimmer stars where the zone squeezes in close. If these planets are just inside or just outside that sweet spot, their habitability is not a yes or no answer. It is a long list of maybes. Maybe the right kind of atmosphere traps enough heat to keep water liquid. Maybe volcanic activity keeps the ground warm even if the star is weak. Maybe tidal forces generate energy to melt ice beneath the surface. These edge worlds are full of questions, and every answer could make the difference between thriving life and permanent silence. Now imagine being there. If you lived on a planet at the cold edge of the habitable zone, winters would not be just seasons. They would be battles for survival. The sun might hang low on the horizon even at midday, casting long shadows over frozen seas. Crops would only grow in brief bursts of warmth, if at all. Civilizations might build their entire culture around capturing, storing, and worshipping heat. Fire could be sacred, warmth could be wealth, and myths might warn of the endless cold that waits just beyond the horizon. On the other extreme, life at the hot edge would be no less intense. Days could feel like standing inside an oven, with survival hanging on finding shade or burrowing underground. Water might only exist in scattered lakes that evaporate as quickly as they form. Entire societies might migrate seasonally to chase cooler zones, or they might live nocturnally, avoiding the deadly glare of their star. Imagine a sky where clouds are not white and soft, but thick, reflective shields protecting the surface from being scorched. On such worlds, life would adapt to the rhythm of extremes, forever bracing for the day the balance tips too far. And here is the shock. Earth itself is not as safe as we think. Our planet drifts near the inner edge of the sun's habitable zone. If not for just the right level of greenhouse gases and the stabilizing role of our atmosphere, we might already be too hot. 1 billion years from now, as the sun grows brighter, Earth will slide out of habitability entirely. In other words, we are an edge planet too. Life has always been living on borrowed time, trusting that the balance will hold long enough for us to evolve, thrive, and now wonder about others. What makes these edge planets so captivating is the psychology they provoke. Humans love thresholds. We are fascinated by borders, by cliffhangers, by things that are almost but not quite. These worlds are the cosmic version of that feeling. They lure us in because they are close enough to life that we cannot look away, but uncertain enough to keep us restless. They reflect our own story, fragile, precarious, built on conditions we did not control but got lucky enough to inherit. And here is the tease. The next great discovery may not be an Earth twin basking safely in the middle of a perfect zone. It may be a planet right on the line, a place where life is forced to bend, adapt, and cling to existence in ways we cannot yet imagine. A planet that challenges our definition of habitable and dares us to expand it. Edge worlds are not failures. They are reminders that life is stubborn, creative, and maybe far more resilient than we think. Somewhere out there, on a frozen twilight world or a scorched borderland, life could already be writing its own story on the thin margin between survival and extinction. Mini-Neptunes. You are staring through a telescope at a world larger than Earth but smaller than Neptune. At first glance, it feels familiar, maybe even comfortable. Not a massive Jupiter, not a tiny rocky sphere. But as you zoom in, the comfort fades. This is not a place with continents and oceans. This is a mini-Neptune, a strange class of planet that sits in a size range our solar system does not even have. And that gap makes them some of the most mysterious worlds we have ever found. Here is where it gets shocking. When astronomers started discovering exoplanets in the thousands, they noticed something strange. The most common type of planet in the galaxy is between about 2 and 4 times the size of Earth. Yet in our own solar system, there is a complete absence of these planets. We jump straight from Earth to Neptune. It is as if nature skipped a step here at home, but built countless others everywhere else. Mini-Neptunes are cosmic middle children, and the fact that we have none means they could be hiding secrets we are blind to. So what exactly are they? Imagine a rocky or icy core, wrapped in a thick envelope of hydrogen and helium gas. Some may look like scaled, down versions of Neptune, cloaked in clouds and haze, with no solid surface you could stand on. Others may straddle the line, holding on to dense atmospheres, but with rocky material underneath. That is the puzzle. Are they gas dwarfs with bloated skies, or super Earths in disguise? The truth is, they could be both, and that uncertainty makes them incredibly important for understanding how planets form. Think about what it would feel like to visit one. If you parachuted down into a mini-Neptune, you would never land. The atmosphere would grow thicker, hotter, denser, until pressure crushed your body long before you touched anything resembling ground. The clouds might glow with exotic chemistry, methane giving the air a blue tint, hazes scattering light in eerie purples or greens. Storms could churn for centuries, driven by heat trapped in the deep layers. To us, they look uninhabitable. But what if life does not need to stand on solid ground at all? What if it floats? Here is where things get fascinating. Some scientists speculate that mini-Neptunes could evolve into something else entirely. If they orbit close to their stars, the intense radiation might strip away their outer atmospheres over billions of years. What would remain could be the exposed rocky core, suddenly revealed as a super Earth. That means mini-Neptunes might be stepping stones in planetary evolution, transitional stages that blur the line between gas giants and terrestrial worlds. When we look at them, we may be catching planets mid-transformation, frozen in the act of becoming something new. And here is a thought that should stop us cold. If most planets in the galaxy fall into this category, then the typical world out there is not Earth-like at all. It is a mini-Neptune. In other words, our idea of a habitable planet, rocky surface, oceans, breathable skies, might be the exception, not the rule. If you were to point to a random star and ask what kind of planet is most likely circling it, the answer would not be Earth. It would be something we have never stood on, never touched, never truly imagined living on. But do not dismiss them as sterile gas balls just yet. If a mini-Neptune is massive enough to hold on to thick water vapor layers, its atmosphere could hide oceans deep below the clouds, oceans larger than anything on Earth. Picture a hidden sea, buried under crushing pressure, stretching across an entire planet. Life, if it exists there, would never see the stars, never know the surface. It would live in perpetual twilight, evolving in an environment that defies every rule we take for granted. It is unsettling, but also thrilling. Because if life can exist there, then life can exist in far more places than we ever dared to believe. And here is the human side of it. We are biased toward what we know. We call planets habitable only if they look like us. But Mini-Neptunes challenge that bias head-on. They force us to admit that our definition of habitable may be laughably narrow. Just because we cannot walk on the surface or breathe the air does not mean something else cannot thrive in layers or oceans we will never touch. These planets expose our arrogance. They ask us to widen the lens. The tease is this. As telescopes like the James Webb Space Telescope keep refining their instruments, Mini-Neptunes are some of the first worlds we will be able to study in detail. Already, hints of exotic atmospheres have appeared. Water vapor, unusual hazes, signals we are only beginning to decode. Every spectrum we collect could be the start of a revelation about what planets are, what they become, and whether life has ways of existing we cannot yet imagine. Mini-Neptunes are not the worlds we expected, but they may end up being the most important. So when you hear the word exoplanet and your mind jumps to Earth 2.0, pause for a moment. The truth is, most of the galaxy is not Earth. It is stranger, thicker, cloudier, more alien, and the most common stage on which the drama of life might play out may not be a twin of our home at all, but a mini-Neptune drifting in the dark, carrying secrets under skies we have never seen. Dying worlds? Imagine a planet that knows its own death is coming. It does not explode, it does not vanish in an instant. Instead, day after day, year after year, it is slowly pulled apart by the very star that once gave it life. These are the dying worlds, planets being consumed by their stars, caught in a slow-motion catastrophe where survival is impossible and the end is certain. Here is the shocking truth. This is not science fiction. Astronomers have already spotted the remains of planets being devoured. In some systems, telescopes have caught rings of debris, trails of dust, gas, and shattered rocks spiraling into the glow of a star. In one haunting case, a white dwarf star, the cooling corpse of what was once a sun-like star, showed chemical fingerprints of a planet it had already torn to pieces and swallowed. Planets do not simply orbit forever. Gravity, radiation, and stellar evolution guarantee that one day many of them will fall. Think about the drama of that. You have a planet circling peacefully for billions of years, growing oceans, mountains, maybe even life. Then the parent star begins to change. If it is sun-like, it will swell into a red giant, its outer layers ballooning outward until they scorch or engulf nearby worlds. For planets too close, the atmosphere strips away first, blasted into space. Then the crust melts, rivers of magma replacing rivers of water. Finally, tidal forces begin to rip the entire planet apart, scattering it into glowing fragments that spiral down into the star like sparks from a fire. It is slow, terrifying, and unstoppable. Now picture what it would feel like to live on such a world in its final stages. Imagine standing on the surface and watching your sun grow larger each day, not as a poetic metaphor, but as a real physical threat. The sky would shift from familiar blue into a harsh, burning red. Temperatures would climb past anything life can endure. Oceans would boil, air would thin, and cities, if any existed, would collapse under relentless heat. And even if life found some way to adapt, it would only be delaying the inevitable. The star is not just your source of light anymore. It is your executioner. Here is the validation. Earth itself is destined for this fate. Our sun is stable now, but in about 5 billion years it will swell into a red giant and bake our planet beyond recognition. Mercury and Venus will be swallowed whole. Earth may or may not be engulfed completely, but either way, it will be sterilized. Even Mars, that frozen frontier, will not escape. The future of our world is to be consumed, either burned into a cinder or torn apart entirely. When we look at these dying planets elsewhere, we are not just studying them. We are staring at our own future. But what makes this even more fascinating is the resilience hidden in the story. Not all planets die in silence. Some put up a fight. Astronomers have observed worlds that orbit so close to their stars that their atmospheres are literally being blown away, leaving behind long comet like tails of gas. These planets are evaporating in real time, shedding material like ghosts, leaving trails behind them. Others may lose their outer layers, but leave behind dense metallic cores that survive as scorched embers circling the star. In a way, the death of a planet does not erase it completely. It transforms it into something new. And here is the psychological weight of this. We tend to think of planets as permanent, eternal, solid. They feel like the background of the universe, the stage, not the actor. But dying worlds remind us that even planets are fragile. Even planets have lifespans. They are not carved in stone forever. They are temporary, like everything else. That realization changes how we see our place in the cosmos. The ground beneath our feet feels eternal, but in truth, it is already marching toward an end. What if civilizations lived on those dying planets? Would they watch their skies with dread? Would they build myths around the growing star, worshipping it as both God and destroyer? Or would they try to escape, launching themselves into the void before their time ran out? It is impossible not to wonder. Because if life has existed out there long enough, then somewhere, someone has already faced this ultimate deadline. Somewhere an alien species has looked up and realized their world was burning away, and they had only two choices: flee or perish. And here is the tease. The more we study dying worlds, the better we can understand the life cycles of planets and stars. Each fragment of dust we measure, each trail of vapor we analyze, is like a glimpse into the future of our own solar system. One day, if humanity survives long enough, we will have to face the same reality. The sun will demand its due, and just like those planets out there, Earth will slowly be pulled apart by the very thing that once gave it warmth and life. The only question is whether we will still be here to see it happen, or whether we will have already written our escape into the stars. Iron planets. Picture standing on a world where the very ground beneath your feet is not soil or stone but metal. A planet built almost entirely of iron, dense and unyielding, its surface gleaming with raw metallic planes stretching to the horizon. These are iron planets, worlds so heavy with metal that they flip everything we think we know about planetary nature. Here is the part that makes your brain stall. We actually believe these planets are out there, orbiting other stars right now. They are not made-up stories, not some fantasy from a science fiction novel. The physics makes sense. When solar systems are born, collisions happen. Planets smash into each other, and when they do, lighter materials can be stripped away, leaving behind only the dense metallic core. Imagine Earth losing its crust, losing its mantle, and leaving just its iron heart behind. That would be an iron planet, a survivor forged in violence. And it is not entirely alien. We already live above an iron core. Earth's heart is a solid ball of iron and nickel, spinning, generating our magnetic field, protecting us from cosmic radiation. Now imagine that inner heart expanded outward until it is all that remains. No granite mountains, no ocean basins, just an endless metallic world, a planet reduced to its essence. That is what these places would feel like: brutal, stripped down, pure. But here is the shocker. These planets would be so dense that their gravity would feel crushing compared to Earth's. A world only slightly larger than our own could weigh several times as much. On the surface, walking would feel like dragging your body through lead. Jumps would barely leave the ground. Falling would be deadly, with gravity pulling you down at terrifying speed. Just existing there would be exhausting for creatures like us. And yet, if such a planet orbited in the right zone around its star, the surface could be stable, solid, even hospitable in a strange way. Think about the night sky above an iron planet. If it had an atmosphere, the sunsets might look familiar. But if not, you would be staring through a thin veil or none at all, gazing directly into the stark brilliance of nearby stars. The metallic planes might glow faintly red with reflected light, or sparkle like dull mirrors. The silence would be overwhelming. No trees rustling, no water flowing, just the hum of your own breath against the void. Here is where things get validating. We have clues that metal-rich planets exist because of the stars they orbit. Some stars show unusually high concentrations of heavy elements, and planets forming around them could inherit that metallic abundance. Scientists even suspect certain exoplanets discovered so far may already fit this category. One candidate, orbiting a star called Kepler-17, appears to be almost entirely iron, the result of a massive collision that stripped away its lighter material. That is not just a theory anymore. That is evidence. Now think about what an iron planet means for life. On Earth, we depend on cycles of water, carbon, and oxygen moving between ocean, atmosphere, and crust. But on a metallic world, those cycles might not exist at all. Without volcanoes releasing gases, without tectonics recycling minerals, life as we know it could struggle to even get started. Yet what if alien life there is not like us at all? What if in that extreme environment, chemistry takes another path? Maybe in pockets of trapped atmosphere or deep fractures in the surface, unique forms of life could emerge, clinging to niches that seem impossible to us. And then there is the human dream. Imagine discovering an iron planet and realizing what it offers: endless reserves of metal, enough to build starships, cities, orbital stations, entire civilizations. For a species hungry for resources, an iron planet is a cosmic jackpot. The catch is surviving the crushing gravity and hostile surface. But we know humans. We have always been drawn to places that challenge us. If one day we set foot on such a world, it might not be to settle. It might be to mine, to extract, to build. Iron planets could be the fueling stations of future galactic empires. Yet there is something haunting about them too. They are planets born from destruction, forged in catastrophic impacts, their softer layers torn away. They are reminders that creation and violence in the universe are inseparable. Every iron planet is a scar, a record of cosmic war, and standing there, looking out over a horizon of endless metal, you would feel that history pressing in. The weight of billions of years, condensed into a single, unyielding world. And here is the tease. With better telescopes scanning the skies, we may soon be able to confirm the first definitive iron planet. The moment we do, it will change how we think about worlds in general, because it will prove that planets are not just blue spheres like Earth or gas giants like Jupiter. They can be stripped down skeletons, cores turned outward, survivors of unimaginable collisions. And knowing that, we will look at our own planet differently. Earth's iron core is hidden deep below. But out there, Entire worlds wear their hearts on the outside. Exomoons. Imagine standing under a sky where your sun is not the brightest thing you see. Instead, it is the giant looming face of a gas planet filling half the heavens, its swirling storms glowing with reflected light. You are not on a planet at all. You are on a moon. But not like our barren little rock. You are on an exomoon, a world orbiting another world, far beyond our solar system. Here is the shocking part. Astronomers think exomoons could outnumber planets. Think about that. We have already confirmed thousands of exoplanets circling other stars, and if even a fraction of those have moons, the real number of potential worlds multiplies dramatically. And not just small, icy rocks either. Some exomoons could be massive, even Earth-sized. Imagine a habitable moon orbiting a giant planet in the habitable zone of its star. That means whole environments, oceans, forests, maybe even civilizations, could exist in places we have not even begun to seriously explore. Let that sink in, because right now, we cannot even confirm most exomoons. They are just beyond our current instruments. We catch hints of them, tiny dips in starlight, shadows where they might be, gravitational wobbles that whisper their presence. But the technology to see them directly is still being built. So we live in this strange moment where we suspect whole classes of worlds are out there, but we cannot yet prove it. It is like staring into the ocean at night and knowing the whales are there even if you cannot see them breach. But we already have a model right here at home. Look at Jupiter's moons. Europa, with its hidden ocean beneath ice. Ganymede, the largest moon in the solar system, even bigger than Mercury. With volcanoes spewing fire into space. If our single gas giant carries so many fascinating moons, imagine what a super Jupiter in another system could hold. Entire families of worlds, orbiting one enormous parent, each moon with its own story, its own environment, its own potential for life. And here is where it becomes even more astonishing. Moons have an advantage planets do not. Tidal heating. The gravitational pull of a giant planet can knead a moon from the inside, keeping its core warm, driving geological activity, and sustaining oceans of liquid water even far from the warmth of a star. That means exomoons could be habitable in places that seem utterly hostile. A moon circling a gas giant at the frozen edge of a solar system might still have oceans and climates stable enough for life. These are worlds that cheat the rules, living outside the neat boxes of habitable zones. Now picture what daily life would look like on such a place. Nights broken not just by starlight, but by the glow of a massive planet hanging permanently overhead. Eclipses happening regularly as the moon passes into its giant's shadow, turning everything into an eerie twilight. Tides rising and falling, not only from the distant star, but from the monstrous pull of the nearby planet. Civilizations here would grow up with skies that remind them constantly that they are not alone. The concept of one world, one home, might not even make sense. Their identity would always include the giant above them, and this is not just imagination. When we think of habitable worlds, we usually focus on planets. But the truth is, exomoons may be even more promising places for life. They could vastly outnumber habitable planets. They could be more stable thanks to tidal heating, and they could exist in systems we already know about, like Kepler 1625, where a suspected exomoon the size of Neptune may be orbiting a giant planet. If that turns out to be true, it will be the first confirmed exomoon, and it will open the floodgates for discovery. Here is the validation that hits closer to home. Even in our own solar system, The places where life might exist are not the planets but the moons. Europa, Enceladus, Titan. These are the names scientists bring up again and again when talking about alien oceans and the possibility of life. If our solar system hides such potential in its moons, then surely other systems do too. The logic is overwhelming. Life may not be bound to planets alone. It may thrive on worlds orbiting worlds. And this is where the tease lies. In the coming decades, new telescopes will finally give us the power to detect exomoons with confidence. The James Webb Space Telescope is already pushing us closer. Future observatories will look not just for planets, but for their companions. And when we find the first exomoon with an atmosphere, with oceans, with the chemical fingerprints of life, it will completely reshape the way we imagine the universe. Because suddenly, every giant planet we discover is not just one world. It is a system that might carry hidden Earths among its moons. So the next time you look up at our own moon, imagine it not as a lonely companion, but as a clue. A reminder that elsewhere in the galaxy, moons may be more than barren rocks. They may be the true havens of life, circling silently around giants, waiting for us to finally see them.